All right, let's go do some nerd math. This course is going to be sort of a practical exploration of the math concepts that go into what underlies most of MOPs. And the vast majority of it is linear algebra, which is things like vectors, matrices. It's essentially how computers handle all of the transformations that you apply to points. And by transformations, I mean, translate, rotate, scale, all the things that MOPs is doing quite a lot of, and all the things that computer graphics do as a whole. So a lot of this stuff that I'm doing with MOPs, it's nothing new. This is stuff that computers have been doing for 3D graphics for a very, very, very long time. But a lot of artists coming into 3D aren't taught these things really. They're just sort of taught like, parent these things together, but they don't tell you like, what is parenting? What does it actually mean? And a lot of this math also applies to things like shaders. And especially when we start talking about vectors and some of the things that you can do with them, like it all ties together really nicely. So having a practical understanding conceptually of what's going on under the hood is going to help you in a lot of different ways during your time as a 3D artist. I've opened up in the example files, which I hope you all downloaded that I posted yesterday. I'm going to open up O1 vectors. And this course is going to be a little bit more paint by numbers in the sense that I'm not going to drop down every single node because none of the networks are really that complicated. It's going to be more about sort of visualizing things. And then there's going to be a few instances where we're going to step in and do a little bit of Vex just to like solidify some of these math concepts. So let's just jump right in. So all of these concepts are linked, but they build on top of each other as layers. And with math, unfortunately, there's no way around it. Like you have to take concepts and layer them and layer them and layer them before we can get to the good stuff. So I'm going to start with something that you guys probably already know and is a little bit boring, but we're going to talk about vectors first. And so if you open up vector basics here and go to visualizer 1, a vector is a direction and a magnitude. So all it's doing is saying, it's an arrow of a certain scale that's pointing in some direction. And the way that you typically think about vectors is as a direction pointing out of the origin. Although you'll find out very soon that it doesn't necessarily mean that conceptually in the same way when you're talking about things like position vectors. If you grab this simple Vex node and just drag the scale around or drag the vector direction around, you'll see that all it's doing is it's an arrow and it points to a certain point in space. So I could say, negative 1.2 here, and you can see that it's pointing to negative 1.2 and it's 1 in Y. It's a point in space. There are different reasons why you might want to look at this as being a point in space rather than a direction. It kind of depends on, again, there's multiple ways of looking at each of these things, and sometimes it's easier to look at it in one way versus another. But the important basic part here is that we're looking at a direction and a magnitude. That's a vector. We're going to use these everywhere. So let's go to the next visualizer here. Normalizing a vector is something that you hear a lot when you talk about normalized normals or a normalized velocity vector or whatever. And all normalizing means is that you're dividing something by its own length. And the reason why you do this and the reason why normalized vectors are so important is when you're dealing with things that involve direction rather than position in space. A lot of the computations that you do on vectors when you're trying to figure out like what way is something facing or how do I rotate this angle to meet this angle, a lot of those calculations are way easier to do when your vectors are all unit length, meaning that they're exactly one unit. So you're effectively operating in a sphere. So you can see that when I normalize this vector, regardless of the scale of it, it is pointing in exactly the same direction. Anytime you're dealing with orientations, you need normalized vectors. And when you're doing any kind of math operation on these vectors later on, when you're trying to figure out anything that involves orientation rather than speed or position, you're going to want to normalize the inputs and possibly the outputs of those operations. If you don't, you can get some pretty weird results. So just keep that in mind when you're doing any kind of vector operations that involve direction. Let's go to visualizer 3 here. Adding vectors is something you'll do pretty frequently, and literally all you're doing is just adding up all of the individual components. So in this visualizer, the red vector is A and the blue one is B. And if you go to the add vectors here, most of this is just stuff for visualizing, like everything under here. But you have vector A, vector B, and then vector C, the white vector is A plus B. So you can move these around if you want like a quick visualizer of what's happening. But you're literally just adding the various components together. In practice, when you're working in Houdini, you'll add vectors when you're doing things like accumulating velocity, or there's a few other situations where you'll do it. But you'll find subtraction happens a lot more often. And the rules, addition and subtraction are very closely related. The rules are largely the same. If I go to visualizer 4 here and then just grab this, you can see that, again, I'm subtracting A minus B here, and the result here is C. Subtraction happens a lot more often because let's say you want to aim something at something else, or you want to, sort of guide a vector towards another point. The way that you find the direction from A to B is generally through subtraction. And let me just show you what I mean here. I'm going to do some, let's hope this annotation thing here works. If you look at this and you say, okay, here's vector A, this red one, and here's B, this blue one, and the white one coming out from the origin looks like it, it doesn't look like it's quite necessarily related. But if you sort of move this third vector up here and look at it this way, I hope that makes more sense, where if you're trying to basically say, what is the difference between these two vectors? You're literally subtracting, how do I get from A to B? This vector is telling you that. You'll be doing this a lot more often when you're trying to figure out a goal, for example, for a particle, or if you need to aim something at something else. Looking at subtraction this way can sometimes help sort of drive home the point of this is how you're going to relate vectors a little bit more closely as opposed to addition. I have to turn off this draw thing. Okay. So that's the very basics of dealing with vectors. A lot of the more interesting stuff comes when you start doing vector products, which is what we're going to go into next. There's two products between vectors that you're going to hear talked about all the time. The simpler one is the dot product. And what the dot product is I've got to clear that arrow off, don't I? The dot product is a ratio between vectors. That's the easiest way to look at it. And what it's doing is it's returning, when you're dealing with normalized vectors anyways, it's giving you a value between 1 and -1, depending on how similar the two vectors are. So if right now I have just vector A here, which is pointing towards positive Z, and vector B pointing towards positive Y. And if you grab this visualizer and just rotate, around X is probably the easiest one for this example. If you rotate these vectors around X, you can see that you're getting this number that's roughly between -1 and +1 based on how similar they are. So if they're parallel, you're going to get a value very close to or equal to 1. If they're perpendicular, you're going to get a value around 0. And if they're exactly opposite each other, you're going to get a value of -1. There's a lot. The dot product shows up everywhere in computer graphics, and it's really important because the way that you compute the dot product is deeply involved in a lot of other parts of vectors, like how you compute sides of triangles and things like that. And we're going to build on this shortly, but it shows up everywhere, and it's really important to know sort of basically what it's doing is you're really just figuring out how far apart in angular terms are these two vectors. And again, the dot product can be and is often used on vectors that are not normalized. But generally speaking, you want your vectors to be normalized when you're doing this calculation, or you're not going to get a -1 to 1 range. You're going to get something else. And there are reasons why you might do that when you're doing things like projections, which we'll get into in a second. But again, keep in mind when you're comparing the angles between vectors, when you're trying to compare them like this, when you're talking about vectors as directions, not as positions, keep them normalized. Let's go to the next visualizer here. So another thing that you can do with a dot product is you can literally project vector B onto A. This is useful for when you're doing things like projecting something onto a plane. Or if there are other reasons why you might need to project these that are a little bit more complicated that we'll sort of touch on later on. But if you look at the projection Vex code here, what I'm doing is I have vector A and vector B. And for C, what I'm doing is I'm computing the dot product again, but I'm computing the dot product between A and B. So what I'm doing with vector C here, which is the white one, is I'm computing the dot product between the two, which sort of figures out that ratio. And then I'm multiplying vector B, the blue one, by that ratio. And you can see that what I end up getting is this projection of this red vector, vector A, onto B. And you can see this a little bit more clearly if you try adjusting these values a little bit. Let's say I move this up. You can see that it's literally just projecting onto sort of an infinite version of that blue vector. And if I move B around, like for example, if I move it onto X, you can see that it leans to stay parallel with it. So this is something that's going to come up a lot too when you're trying to, there's situations where you might want to project a point onto an imaginary plane a certain distance away. Dot product also comes in handy there. So this might seem a little bit abstract, but we're going to sort of build on this concept of projection and comparing vectors later. Let's get into a slightly more complicated example here. The dot product is also used a lot in shading calculations because when you're comparing angles of things, that comes into play when you're, for example, illuminating something. A lot of the simplest illumination models in computer graphics are based on the dot product because the ratio between the direction a surface is facing, which is the surface normal, and where a light is sort of implies how bright an area is going to be shaded at that point. So I'm not going to go over this entire network, but basically what I'm doing is I'm bringing in like the point light icon and then transforming it and moving it over here. So I have a control here that's using the point light.bgeo. So it's just this is to build an icon. That's all it is. And I'm transforming it. So this is so that I can rotate it basically. That's all this is. It's a really quick visualizer. So the first thing that I need to do here to do the calculation, and just to give you an idea of what's going to happen at the end here, I have this sphere and I'm going to illuminate it, and I'm going to do it using the dot product. So what I want to do is first get the light angle as a vector, right? So where is this in relation to the origin? Because the direction of the light is what matters when doing this shading calculation, more so than the position would be for like fall off. If we're trying to do light decay, we're not worrying about that for this example. So what I'm going to do is get the position of this light. And so I merged in this point here up top because I have just a single point right in the center, and that's 0.0. So that's what I'm going to grab is the position of 0.0. So I'm going to say vector n is equal to 0.0. I'm getting the attribute p, and I'm getting that attribute from 0.0. And then I'm just going to save this. I'm going to bind this to the normal attribute for this object. So I'm going to say at n equals normalize and that local variable that I just made. So this is running in a detail wrangle. So what I've done is just created, because I only need to do this once. It's going to be the same. I don't need to run this over every point. And so I have right now is a vector where it's equal to 1 because this light, the normalized vector here, is on positive z. Now to actually apply this to the points in the sphere, what I want to do is take that vector and compute the dot product between that vector and the surface normal of the sphere. So I'm going to run this on points for the sphere because it needs to apply to every point on this. And the first thing I want to do is grab that normal that I just computed. So I'm going to say vector n, or let's call this cam n to differentiate it from local, is equal to detail. And then I'm grabbing this from the second input here, like where I just computed that other normal. So detail input 1, and then I'm grabbing the n attribute I just created. And then I'm going to say float dot, because the dot product is a scalar. You'll sometimes hear the dot product actually called the scalar product instead of as opposed to the vector product or the cross product. And that's because the dot product between two vectors is a ratio. It's a single number, a scalar. So anyways, this is equal to the dot product in Vex between the normal of this sphere for each point and that camera normal. So now I have a ratio between the direction of the light coming in and the surface normal for each point. What I'm going to do now is with typical shading calculations, you usually cull back faces. You don't see them at all. And if you remember from that first example, if the dot product is less than 0, the two vectors are basically pointing in opposite directions, meaning it's going completely away from the light. We're not going to see anything there. That's in shadow. So what I'm going to do is I'm going to clamp this value between 0 and 1, because if the value is -1, I don't care. It's just going to be 0. It's not shaded. So I'm going to clamp dot between 0 and 1. And now what I want to do is just say the color value of each of these points in the sphere is equal to, I'm just going to ramp this because I like ramps, it gives us a lot of control. I'm going to look up a ramp by this 0 to 1 value. And one little trick when you're doing CH ramp, if you've ever done this on a node and then you click this little button here to auto generate parameters, if you do this normally, tramp by default is going to return a float, which is fine for this because it would just give you black and white values anyways. But if you really want to make a color ramp, if you force this to be cast as a vector when you write this operation, this automatic parameter generation button will actually give you a color ramp. So just real quick trick. Otherwise, you would have to actually go into the parameter interface for this, click on the ramp, and then change it from float to color. So this is just a shortcut for that if you're just trying to bang out Vex really quick. So now that we're here, let's go back to this highlighted transform node and then just try rotating this around. And you'll see that what you're getting is this sort of very, very basic illumination of this sphere from this, this fake light that we built. And as it turns out, this is Lambert shading effectively. There's like a couple other nuances you might have to worry about, but when you're talking about the very simplest core idea of Lambert shading, it's the dot product between the light angle and the surface normal. Next example real quick, this is another similar thing that you'll often see done with the dot product in shading, is the idea of like a Fresnel or a X-ray shader. So if I go here, again, I left this code out, but we're going to do effectively the same thing, but just sort of change the terms a little bit. Let's say that instead of this being a light, this is a camera, and I'm looking through this, and I'm just going to reset the transform so we're looking straight down Z to make this easier. So again, the code is almost exactly the same. I'm going to grab, instead of a light normal, we're going to call this a cam normal. So I'm grabbing the detail attribute of input 1 here. I'm grabbing the N attribute, so the position of that same thing there. I'm going to compute the dot product between, so dot between each point on this peg head and the camera normal. I'm going to clamp it. This is really the code, same code as before, but I just want to type it again to drill it home. And I'll wrap this up as a vector the same way to make sure that the parameter interface autocasts it as this. And what you can do here is if you reverse these and then look at it through the camera, this is looking straight down Z, so this is what your imaginary camera would be seeing, and then kind of bend this a bit. What you can see is that the areas that are perpendicular to the camera, so where the normal is facing orthogonally to the camera, you get these highlights. So it's highlighting edges relative to the direction that you're looking. And this is something that you'll see a lot on the so-called Fresnel shaders or shader like sheen, velvet shaders, things like that. It's a really common fake that people will add to real-time shaders. And in the old days, we used to do this a lot to shaders that didn't have fancy BSDFs like we have now, where you can just get this kind of extra sheen. You know, if you're trying to describe a material that's very velvety, it'll often have, because of the tiny little hairs on it, it'll have this kind of extra lighting on the edges. And all it is a dot product calculation. In Maya, this is like what the facing ratio, if you do the sampler info facing ratio node, that's all this is doing. So all of these things are very common throughout computer graphics. We just call them different things. But under the hood, it's the dot product between the camera and the surface normal, and then just sort of taking that resulting value and bending it somehow to make what you want. So the next thing to talk about before we start getting a little bit weirder is the cross product. And if you go to the first visualizer here, the cross product is an operation that essentially gets you an orthogonal vector to the two vectors that you put in. And by orthogonal, it just means perpendicular. It's not opposite in that you're not just flipping it, because for that you just multiply a vector by -1. It's finding something that points in a direction that neither of the other two can ever point in. That's sort of what orthogonal means. If you go up here to cross vectors and you start playing with these values underneath, you can see that, I don't actually want to scale this. You can see that what it's going to try to do is just find something that points in exactly the direction that the other two doesn't. So if I manipulate these a little bit, you can see that it's adjusting that third white vector based on what's going in. And something else worth noting here is that you see that when these vectors start getting skewed, that the cross product is getting longer. This is also another operation that's very vulnerable to vectors that are not normalized. If you click this little checkbox here, this normalizes the input vectors, and you can see now that you're getting unit length vectors for this whole thing. So again, you're dealing with vectors and you care about orientation, make sure that your inputs are normalized. And if you look at this Vex code up here, all it's doing is it's taking in your input vectors, A and B, and saying, if that box is checked, normalize both these vectors and then cross them. That's all this is doing. So it's, if you're doing cross products, on paper, it's a little bit more effort to get this done, but conceptually it's very simple. Given two input vectors, find a third that doesn't point the same way. And this is something that we're going to do a lot when we start dealing with matrices and rotating things, because something you might note here is that if we wanted to, for example, rotate this red vector onto B, this third vector here would be a very convenient axis of rotation between the two, right? So like you can imagine that I'm taking this red vector and spinning it to point to vector B, and it would be spinning on that white axis. So you're going to start seeing this a lot when you want to find out how to rotate one thing onto another. Let's go to the next visualizer here. So what this is doing is, and you might notice that this is pointing in a different direction from before, try rotating vector A around Y. So right now it's at -90 degrees, but just try grabbing this and rotating it. Maybe I'll do a little bit slower and see that you can see that as it crosses this line, vector C starts getting unstable. It's not really sure what to think. And it flips at some point. This is because the cross product is not commutative, meaning that the terms that you put in, vector A, vector B, if you switch them, you'll get a different result. The exact order of the result that you get is dependent on something called the right-hand rule, which is worth Googling, but it's a simple concept. It's basically saying that for a coordinate system in computer graphics, there's sort of some coordinate systems are left-handed and some are right-handed. And what that means is basically just if you have vectors A and B on and you imagine that your hand, your thumb, and your first two fingers are these vectors. If you cross them, what direction is that resulting vector going to be? So if you're crossing your index finger and your thumb in a right-handed coordinate system, that third vector is going to be coming out towards your middle finger. In a left-handed coordinate system, it's going to do the opposite. There are computer graphics programs out there that are left-handed. I want to say that Unity might be a left-handed system. I could be wrong there, and there are others, I'm sure. Houdini is right-handed, and a lot of other computer graphics uses right-handed coordinate systems. You might have run into this before if you're trying to directly translate polygons from one DCC to another, and you notice that like normals get flipped for some weird reason, or like your objects get scaled in weird ways. That's why. The other thing to note about this is that, again, if I start rotating these things so that these vectors are almost facing each other, just undo this rotation that I just did, you're going to hit a point when they're too close together that they become unstable and freak out. And if I go even slower, you can see that there's going to be this this time in the middle where it's not working as well as I wanted it to. But basically, the reason that you The reason I'm bringing this up is because if you have two vectors that are almost or are actually parallel to each other, and you're trying to find an axis of rotation, cross product between the two, there eventually comes a point where it's indeterminate. You're not going to find anything useful. Where you might have seen this in practice is when you're dealing with something like an aim constraint. If you've ever made an aim constraint before, you'll notice that you need a forward vector, like your aim vector, and an up vector in order to solve an aim. And you'll notice that if your objects are passing right over each other, you'll get some possibly popping or flipping behavior as that thing crosses. The reason for that is because of this property of the cross products. Like it becomes increasingly difficult to get you a stable solution as those two vectors converge. And then once they go in the opposite direction, it flips. So keep that in mind. This is why that behavior happens, and knowing about it and carefully determining where your up vector is and making sure that it's as orthogonal, as different from the normal vector or your aim vector as it can be, means that you're going to get more stable solutions to these problems. This next visualizer here is sort of another practical application of what you can do with the cross product. There's something that you might have heard effects artists talk about, where they call it like the double cross, or sometimes the double cross product. And what it is a way that you can kind of manipulate normals on a surface in order to get interesting behavior for particles, or for sometimes other things. So to really quickly go through this example, I have a line here, and I'm resampling it and then using guide process to bend it along one axis, and then copying it so that I get this sort of funnel shape. I'm going to skin it into a surface and then reverse it. So now I have this funnel where the normals, if I turn them on, are pointing out this way. I'm going to compute normals on points so that I have one normal vector per point instead of the default vertex normals. So you can see how they're all facing here. So let's go down to this point wrangle here. And what I want to do is kind of show you what the cross product does on polygons. So let's say that I want, I want a force that's going to kind of swirl around this funnel, right? And I've got these normal vectors pointing this way, but like, how would I rotate them so that they are swirling around something? And the cross product is going to come in handy here. What I can do is I need to define sort of what the axis of rotation is going to be to rotate these normals into the position that I want. And a lot of the time, an easy way to do that is to just figure out if you imagine this being a cylinder force or a vortex force, what is that axis going to be? I'm just going to use world up for this example. So I'm going to say up equals, I can just say 0, 1, 0 for this. Or if I want to parameterize this just for an experiment, I can say normalize and then CHV, which means a vector parameter for this wrangle, up. So I'm going to take whatever I put in here as up and normalize it, and that's going to be my up vector. So if you hit this button, you're going to get this parameter added here. I'm going to set that to 1. And so now my up vector is world up, real simple. Now I'm going to say n equals normalize. Again, we want to make sure that our vectors for this are normalized after the fact. And I'm going to cross the normal vector and the up vector. And if I'm just going to go down to this add node so that I'm not seeing the polygons necessarily. But what you can see is now I get this swirl force where these things are sort of following the direction of the surface, sort of rotating around what I've defined as that up vector. And you can see these things kind of leaning. If I adjust this up vector so that it's pointing in different directions, it's going to try and lean around a different axis. But this tube is facing, or this funnel is facing an obvious world up axis, so it looks best here. So the double cross, which is something that I brought up earlier, is sort of doing this twice. So I'm going to go down to this point wrangle here. And what I'm going to do is sort of cross that vector that I just generated again against up, or against n, to get an even different flow. I'm just going to visualize this add node here. Right now, this is going back to our original normals. So again, I'm going to define an arbitrary up vector. So this is going to be just a parameter that I define as up that I'm going to normalize. So we're going to set this to 0, 1, 0 again. And now I'm going to set the new n to be normalized. And then I'm going to, again, cross n against up. But instead of crossing n just against the up vector, I'm going to cross it against another cross product. So forgive me for this. So I'm crossing the normal and the up vector, and then crossing that again against the normal. And the result is going to be that it's going to sort of follow the contours of this along that up vector that I defined. So if you were trying to make like a funnel force where you wanted particles to be sort of following the surface but flowing downwards, the double cross product is a great way of getting that. So basically, I'm finding that swirling force first, and then by crossing that against the surface normal again, it finds the orthogonal vector, which happens to be pointing, it's basically taking the up vector, because I'm starting from up and n and finding the orthogonal vector. So like this third one, and then crossing that again against that up vector is finding the orthogonal vector, which means it basically wants to point down again, but projected onto the surface. So like following the contours of it. This is a really common trick that you'll see a lot that effects artists use, even if they don't really understand what's going on under the hood. Because if you want particle flows to follow things and you don't necessarily want to do that using collisions or whatever, this is a very cheap and effective way to get that effect. So the first cross product is, again, getting you this angle. So if I cross these original normals against, and I'll just put add on this as well so that it's a little easier to see. So here's our original normals, and I'm crossing this against the up vector. So world up pointing straight up, and the orthogonal vector that you get from that is this one. So it's following the contours of the surface, but it's pointing sideways. All of these vectors are more or less pointing along the XZ plane because we're crossed against the y-axis. So everything's been projected onto XZ, but following the direction of the surface. When I take that and cross it against the up vector again, so crossing it against, crossing against the normal again, which is this code down here. If you remember the way the normals are originally facing, and then you take these projected on the XZ plane, what I'm going to get are things that are going to be trying to point down the Y plane. Just do this again. But they're effectively relative to their point position. They're, how do I explain this? This does get hard to sort of describe in words. But they're going to be trying to point down Y, but because of where the original vertex surface normals were on this cone, they're going to be facing along the surface because they're influenced by that normal direction. But it's just a sort of an orthogonal 90-degree rotation from these vectors, right? So this is the first cross product, and then by crossing against the original normals again, we get this orthogonal vector. All right. Well, the trig example here is the second file, and this is mostly just a quick demo. It's not something where we're going to do a whole lot of Vex to fill in. I've just built a few visualizers here to help you with some of the trig concepts that we're going to be using. So if you open up O2 trig and then open up trig basics here, go all the way to the left. So when we talk about trigonometry, if you're not thinking about triangles, the first thing that most people are going to think of is sine, cosine, maybe tangent, if you remember anything from that time of your life. But we think of sine waves all the time. It's like, yeah, line goes up, line goes down. It's real simple. All I'm doing here is computing a sine wave, and then I have some things in here to determine, my amplitude, the frequency, all that stuff. And that's commonly a way that people will think about sine waves, right? You think about it almost like audio. You're probably also familiar with sine and cosine referring to the ratios of the sides of a triangle. Because these things, this is sort of why sine and cosine exists, is to describe the relationships between these angles on a triangle. So I built this little visualizer here where you can kind of see, if you scrub the timeline, that the sides of the triangles change. We have this guy on the bottom here. This is our angle. Like when you talk about solving triangles, you usually are picking an angle, you're picking a corner and saying like, this is theta, right? This is my angle, this is what I care about. And then you name the other sides based on that reference angle that you've chosen. So this guy on the bottom here is my adjacent side, this guy here is my opposite side, and this guy that connects the two is the hypotenuse. So SOHCAHTOA, all that stuff, when you're talking about the sine, sine is the opposite over the hypotenuse. All these things are ratios of triangles and the angles between them. So again, you can kind of move this around and you can see that this angle theta here is a consistent ratio that's solvable based on the lengths of the sides of this triangle. If we go to the next example here, and keep in mind, take a look at these numbers and just sort of keep them in the back of your head as you go to this next example. So rather than just look at this as the lengths of the triangle, you can also look at this as coordinates. So this top point here that's made where 3.4 is the length of one of these sides and 3.66 is the length of the other when we're talking about these blue sides, you can see that these are basically coordinates in a coordinate system if we're looking in 2 dimensions. And something that you'll also notice is that this point follows a circular arc. But thankfully in Houdini, a lot of this stuff will be handled for you, so you won't have to memorize quite as much. Let me lose my train of thought there. So again, this is important to think about this as it's not just the lengths of sides of a triangle. You can also think of this as almost this is a coordinate system, right? Like this point in space is directly related to these lengths of the triangle sides. Now let's go to this next example. So now we're doing a 90-degree rotation. So at the very bottom here, you can see that theta is just about 0, and we're at we're at 5 in coordinate space, 5, 0. We go all the way up here, and now we're at 0, 5 approximately. And you can see that at the very top here, at the top of this arc, the value of theta down here is roughly 1.7. Well, 1.567. And if you were to multiply this by 2, let's just grab a calculator and do it. Let's say 1.567 times 2, and this is rough because this is not mathematically perfect. This number may look familiar to you. This is pi. So what we're dealing with here is a 90-degree rotation. And if you remember from basic geometry that the circumference of a circle is 2 times pi and then times the radius, but we're dealing with unit circles here, so we can forget about the radius. We are dealing with 2 times pi as forming a complete circle. So this 90-degree rotation here in radians, because when we're dealing with angles, most of the time we're dealing with radians because it's much simpler for the math and more precise. We're dealing with a pi over 2 rotation, and that's where this number comes from. So keep that in mind. All of this comes back to the unit circle, which is going to come back to these normalized vectors and everything else. This is all very important when you're thinking about rotations. So one more example here. What I'm going to do is, let's just go back here. And I've run this through a time shift so that we're focused on a very specific point. If you take a look at this Vex here, what I'm doing is just defining vector 1, vector 2 here, and which is derived directly from these points in this visualizer. And this expression here is basically using the inverse of the cosine function. So the cosine of an angle describes the ratio between the 2 sides of this triangle. But if you have the 2 sides already, let's say I already know that my vectors here are 0.53, 3.553, whatever. I know what these vectors are, but I want to find this angle theta. I can turn the cosine on its head, and that's called the arc cosine, or the shorthand in Vex is going to be a cos, and then get the dot product between them, which is the ratio between those 2 angles. Remember, we're talking about ratios with the dot product, so the difference between how these things face. And finding the arc cosine of that gets me that angle theta. this is also going to come up quite a lot. This is basically telling me what the angle between these two vectors are. And if I open up the spreadsheet and go to detail view, because this is a detail wrangle, you can see that theta here is 0.785398, which matches this exactly. So the arc cosine is something that's also going to come up very soon in this lesson, because it is a bog standard way in CG of telling you what is the exact angle in radians for me to rotate one vector onto another. And if you remember, if you want to find the axis of rotation between those two vectors, you have the cross product to solve that. So now we've just found a way to relate the two sides of this triangle or these two vectors in space in a very precise way. This was just a really brief overview. Obviously, trig goes way deeper than this, but these are the concepts that we need to kind of know right now. Okay, great. Yeah, real fast trig crash course. So let's go on to the third section here, which is O3 transforms. And this is where stuff is going to get much more closely related to MOPs and also a lot more difficult. So there's a lot of examples in here. We're going to start at the very top in matrix intro, and then just start here on all the way on the left. So if you're looking at this visualizer here, it's just home selected, and then click on this so that you can see this sort of this matrix toy node. A matrix in the simplest terms, when we're dealing with CG, is a stack of vectors. So when you're looking at a transform matrix like this, these are the input values that I'm putting in, and then I have some controls here to be able to rotate it, to manipulate it, and then these are the output vectors that you would get from that. You can see here that x is equal to 1, 0, 0, y is equal to 0, 1, 0, and z is equal to 0, 0, 1. This is called the identity matrix, or the identity transform, and it's called that because this is basically saying, if you look at these as x, y, z coordinates, it's saying that x is facing x. And you can see that with this arrow if you compare it to this little gnomon at the bottom. Y is facing y, it's facing up, and z is facing z. So it's a transform that's just saying everything's normal. My coordinate space is no different from the world space that we've all agreed on. And you can see that if I drag this theta slider here, it's going to rotate around whatever axis we've picked, and the output vectors are going to change accordingly. So we're going to use this toy a few times to illustrate a couple of different concepts about what matrices are, but it's important to be able to look at them and say this matrix is essentially a stack of vectors telling me which way this shape is, or which way this my local coordinate space is facing relative to the world. So let's go on to subnet 2 here. This matrix is representing a 90-degree rotation around x. So my axis is 1, 0, 0, and theta is pi over 2, which is a 90-degree rotation. Remember, 2 pi is a full circle, so pi over 2 is 90 degrees, a quarter turn. So my input values are the same. This is an identity matrix going in, but my output values, ignore that these are coming in scientific notation and just assume that this is basically a 0, and so is this. This is just because floating point precision always means that your numbers get a little bit weird when you're talking about very small things. But notice that when we do this rotation, x is still 1, 0, 0 because x is our axis of rotation. So that vector isn't changing at all. But y is now facing positive z, and you can see that here when you're comparing it to this gnomon down in the corner. And z is facing negative y. So this is important. I mean, when you look at these vectors and you see these values, it's describing sort of at once an orientation. So like this is how this thing is facing, and it also is potentially describing a rotation from some reference point. In this case, our reference point is world space. It can mean either thing. I hope that's not too confusing, but you need to be able to look at this in both ways. Like either this is a matrix and like this is just its point in space, this is the direction this thing is facing, or this is a rotation that we could accumulate onto something else. And we'll go into that deeper later. Now let's go over to subnet 3 here. And this is just, again, the same visualizer, but I've tied theta to time. And so if you rotate this slowly and just take a look at the numbers that you're getting in the output. So I'm going to go roughly to a 90-degree rotation here. and look at the numbers that we're getting. So y is roughly facing z, and z is roughly facing negative y. And then go back again to about here. And now we've got y facing negative y, and we've got z facing negative z. And then back again. And notice that these numbers, as we rotate, are always oscillating between -1 and 1. You're never going to get past that when you're dealing with normalized vectors, when you're rotating these things. Those numbers should, or those ranges anyways, should seem pretty familiar to you because they are the ranges of sine and cosine functions. When you take the sine of a number, you're going to get a value between -1 and 1. You're taking a cosine, it's the same deal. So this whole sine cosine nonsense from trig is popping up again here when we're talking about rotation matrices, because again, we can describe rotations through sine and cosine. If you remember that visualizer on the trig end of things, where we're taking those two vectors and thinking about it as a coordinate system instead, it all goes back to sine and cosine. That rotation, that transformation that we're applying to that point can be looked at as a rotation from the origin, and that's described by theta, that angle, right? So all of these things are pretty closely linked together. So let's do this with geometry now instead of doing this with this little visualizer here. So what I'm going to do is go over to this pighead here and go down to this point wrangle. And it is totally okay if you don't understand what's going on here, but I just want to fill this out with you so that you can kind of see what's going on here in terms of trig. So I'm going to define theta first. So theta equals ch theta, just like we had before. And now my axis of rotation is x. And I'm just going to say x is 1, 0, 0. Just world x, that's what I'm going to rotate around. Now, what I'm going to do is describe y and z in terms of trigonometric functions. And again, this is not something that you would normally directly do in Vex, but this is, all I want to do is describe the math under the hood, what a matrix is doing when you tell it to rotate around x, because it's very particular. So let's define vector y. And again, we're going to use set because this is how you build vectors in Vex when you're not building them as constants. You use the set function instead of using curly braces. So vector y is going to be, again, 0. But y is going to sort of oscillate in y between -1 and 1 based on a particular trig function. And in this case, it's going to be the cosine of theta, which I'm going to, in the channel that I'm building, I'm going to build it as degrees to make it easier to think about. But we need to convert degrees to radians, so that's why the radians function is here. And it's the cosine of theta, essentially. And then y's z component, because again, the x component isn't going to change because we're rotating around x, is going to be the sine of theta. And then z is going to be very similar, but just slightly different. Again, we're not going to change the x component because that's our axis of rotation. But in this case, the y component is going to be the negative sine of theta. And then the z component is going to be the cosine. So it's a lot of sine and cosine functions with very specific orders sort of wrapped up into these three vectors. What we need to do at this point now is make a matrix out of them. And in Vex, if you want to make a matrix out of a stack of vectors, you can, again, use the set function. So I'm going to say matrix 3M. And keep in mind, a matrix 3 is what we're dealing with right now because we're dealing with a set of 3 vectors stacked on top of each other to describe, in this case, orientation. It's not the same as a matrix, which is a 4x4 matrix. We'll get to that later on. Just make sure you're calling this matrix 3 because the distinction is important. And I'm just going to say set x, y, z. So I'm literally just stacking these 3 vectors on top of each other and making a matrix out of them, just like we had in the matrix toy when I was showing you the visualizer there. Same deal. And now let's, just as a test, I'm going to bind that matrix to a variable so that I can see it in the spreadsheet. Just for curiosity's sake, like so we can see the numbers. I'm going to say 3 at test equals m. In Vex, the prefix for a matrix, a 3x3 matrix type variable is 3. And the last thing that I'm going to do is when you want to transform something by a matrix, whether it's a vector or another matrix, you multiply them. Part of the magic of matrices is that they are straightforward for computers to multiply, especially when they're square. And we're always going to be dealing with square matrices in CG. But if I want to take this matrix that is a rotation in space and apply it to these points, the point attribute P is a vector. So all I have to do is just multiply it by this matrix. So I'm going to say P times equals M. And now I'm going to click this so that I can make this theta parameter. And I'm just going to set theta to frame so that it rotates, according to degrees equals frames. And so you can see that what this thing is going to do is rotate, pivoted around the origin, around the world x-axis. So again, I don't have this memorized. I wouldn't expect anybody to memorize it because this is literally just if you want to do a rotation strictly around X. When you start talking about rotating around multiple axes, you have to start solving slight variations of this matrix for each component. It gets really cumbersome, and this is why you have computers to do this for you. The point here is to try to relate the fact that all these trigonometric functions talking about those sine waves going up and down, -1 to 1, is talking really about circles. And when you're talking about circles and rotating from one point to the other, now you're talking about vectors. That's why, again, everything is talking about a unit circle. So we have this very simplified system that we can use and extrapolate that to finding relationships between vectors. And so much of CG, as we see it, involves vectors, your normals, your point positions, all of that stuff. That's why this stuff keeps coming back over and over again, is because it's all really tightly interwoven. So anyways, I've got this really great spinning pig head. I'm going to just split my viewport really quick here so that I can see here I have a built-in, so I can see the spreadsheet. And if you remember, I bound that test attribute. So let's just stretch it out here. So you can see that I've got these numbers. This is my transform matrix, essentially. This is the matrix that I just built. So again, X doesn't change because that's my axis of rotation. So that's 1, 0, 0. And then as I slide, you can see these things, these values, again, oscillating between -1 and 1 as they go through this rotation process. And what I want to do really quick here at the bottom here is I'm running this through a MOPs convert. So I'm turning this into a packed primitive now. And if I go to the transform modifier here, I'm just doing exactly the same rotation, right? I'm rotating around the x-axis. And I don't have a transform attribute here now that means anything because I've converted this. But if I go to the primitive view and then activate intrinsics and go to transform, you can see that, again, I've got this 3x3 transform, so 9 values. And I'm the x-axis is 1, 0, 0. And it's exactly the same values going across when I'm doing this rotation. So I'm oscillating between -1 and 1 across these various axes. And you can see that the X component of both the Y and the Z vectors that make up this matrix are not changing because we're rotating around X. So this is the math that MOPS is doing under the hood, abstracted somewhat by Vex to rotate something. It's all trig under the hood. Okay, let's do one more here. I want to talk really briefly about scale as well. So we've got another pig head here, and then another wrangle. And what we're going to do is build up a matrix and scale it instead of just rotating. So let's just build out a quick little interface so that we can just type in vectors and get a matrix out of it and see what happens. So I'm going to say vector X is equal to vector channel X, and just do the same for Y, right? So Y equals CHV Y and Z equals CHV Z. There's faster ways to do this, but whatever. Then I'm going to make a matrix 3, call it M, and set it to that stack of vectors, X, Y, Z. And then at the end, I'm just going to say multiply P by that matrix. And then when I hit this button, now I've got the stack, and you can see that everything is zeroed out. I'm going to make an identity matrix to start. So X is 1, 0, 0, Y is 0, 1, 0. And now you can see I've gotten this pancake pig completely flat because Z is 0. And now 1, 0, 0. And now I've got the complete pig again. And you can see that if I scale any of these vectors up, so they're no longer unit vectors, I'm stretching the pig out along that axis. And if I set them all the same, so if I make this 2, 2, 2 down the diagonal, now I've got a pig head scaled up by double. Another thing to notice here is that if you start bending these axes so that they're no longer normalized vectors and orthogonal to each other, you can see that now I'm going to start getting a skew. So this thing is sort of stretched out in weird directions. Scaling matrices is literally just scaling the vectors that go into the matrix. So a 3x3 matrix like this, and this is important, a 3x3 matrix defines both the orientation of something in space, like we were describing earlier, and the scale. So all the sine cosine stuff is mostly handling like rotations, like figuring out which way all of these things are pointing. And then the length or the magnitude of those vectors is determining the scale of the object. And all of those things combined together makes your 3x3 matrix that determines what this thing is doing in space. Okay, so let's go to the next section, and this is aim matrix. So all the way on the left here, what we're going to do is build a very simple aim constraint, right? Essentially what MOPs aim is doing under the hood, but also anything else that does constraints in CG. This is roughly how it works. So I've built out this quick little setup here where I've got a control object. So just this little plus here. I'm packing it. And the only reason I'm doing that is so that I have a single point at the centroid of this. So I can just use this as a control, essentially. And so it's easier to reference in Vex. And now I have a point in space that I'm going to copy something to. And that thing is going to be the pig head. So what I want to do is make a matrix that describes an orientation in space. So I still, again, I need those 3 vectors. But what I want to do is make it so that the vectors are pointing in a specific direction that I care about. This will make more sense in a second. But what I want to do is, and let's template this target. I want the vector that, let's do this annotation thing again. I want the vector that points from this pig head's position to this. And if you remember from a few minutes ago when we were talking about vectors, the way that you can sort of figure out where's the direction of something, like how to like point something at something else, is through subtraction. Get that target position as a vector. So let's say vector target is equal to point, and then 1, because I've got this packed point going into the second input here. So input 1, P, and then it's just 1 point. So that is the position of this little cross in space. What I want to do now is subtract my current position, the position of the pig head, or the point that this pig head is going to be copied to, the single point, from that target's position. Because again, vector subtraction, and I'll scroll over this in a second, vector aim equals normalize. Because again, for orientations, everything's got to be normalized. Make sure you're doing this. Target minus the point position. And so if you remember vector subtraction, I've got this vector here, which is essentially an arrow with no length. And then I've got, why can't I draw? And then I've got, no, you don't like that? It does not want me to switch off of mouse mode. So unfortunately, let's try this again. There we go. So I've got this vector, and what I'm doing is I'm subtracting this minus this. And the order matters. What that's going to do is say that, like, how can I describe it? Subtracting this target minus this makes sure that, rather than the opposite, makes sure that the arrow is pointing this way, because this is my aim direction. And then normalizing it makes it a unit vector. So now it's about this long, and it's going to describe the orientation rather than this full stretched out vector describing the exact difference between them. Okay. So now let's go to the next part. Remember that in order to define a matrix, and a matrix is an orientation, I need 3 vectors, right? I can't just say forward because then that's only one component of that matrix stack, right? We need 3. So if you're used to dealing with constraints in 3D, the other vector that takes part of this is the up vector, right? Like that's the other part that you usually have to define in order to describe an orientation. And this can be really whatever we want in this case. We're not doing anything too complex. So let's say up equals world up 0, 1, 0. So with these 2 vectors, we're almost there. We don't quite have a full matrix stack because we need 3 vectors, right? And when you're describing an orientation for something, generally speaking, you want that matrix to be orthogonal. That means that you're going to get a stable orientation, something that's not going to jitter and flip a bunch. And the way that you do that is finding the orthogonal vector to n and up. And if you remember from before, if you want an orthogonal vector to 2 others, you use the cross product. So I'm going to say vector side is equal to, and again, we're going to normalize, and we're going to cross that up vector against our aim vector. So now we have a stack of 3 vectors, right? The problem with this approach, and it is a problem, but it's solvable, is that, again, I'm going to just activate draw here. Remember that we've got this aim vector here, and we've got this up vector here. These are the 2 vectors that we've described. And our cross product from these 2 is going to roughly be directly along the x-axis. So it's going to kind of be pointing out here. But the cross product of these 2 vectors, and if you look at like if you look at the difference between the aim vector here and the up vector, this is not an orthogonal matrix, right? Like this vector here, the side vector, is orthogonal to these 2, but up and aim are not orthogonal to each other. So we're going to get weird results out of this if we try to use this to describe an orientation. So what we need to do is take another cross product to basically say, we're prioritizing the aim vector in this case because we know that we need the aim to be perfect. What we're going to do is say, okay, this aim and this new side vector, we know that those are orthogonal to each other because we just crossed them. But what we need to do now is cross the up vector again against this aim vector in order to get a third, basically to adjust the up vector so that it's pointing in a way that makes sure that these 3 vectors that make up this matrix are all orthogonal to each other. And that means that we're going to get a stable orientation that's not going to look weird. So again, the way that we do this is through more cross products. So really quick, I'm going to say up is equal to the cross product of the aim vector, which we're prioritizing, and this new side vector that we created. So up is not going to be perfectly world up. It's going to be something else that we made up. Now I'm going to make this matrix. So matrix 3M is, again, we're going to use set, and we're just going to say side, up, aim. The reason for the order is because when you're talking about orientations in Houdini, the normal vector, which you'll often in world space you'll think of as positive z, is the third vector in the series. Like when you think about aiming anything at anything else, the default aim orientation in Houdini and a lot of other 3D software is z. Cameras traditionally in CG point along the negative z axis, but it's always z, at least almost always. So that's why the order here, we're starting with side because that's our x-axis, which is sort of conventionally, this is side. The up axis is relative to y, or world up, so it's our second vector, and then aim is the third. So now we've got that stack of vectors, and we've turned them into a matrix. And so now the only thing that we have to do is turn this into an attribute that copy to points understands. We could, if we wanted to, just define n and up as 2 vector attributes and feed that to copy to points. And copy to points will do this for us. But what I want to do for now is just feed it this raw matrix data and see if our idea here worked. Copy to points recognizes a lot of attributes. There's a whole stack of them that you can view in the help for template point attributes in Houdini. But one of them that it recognizes is a 3x3 matrix called transform. So I'm going to say 3 at transform is equal to this matrix M that we just generated. And now if I go down to copy to points and I commit that vex, you can see that this pig is looking directly at that point. And if I just move this guy around, you should do the same. You can see that he is doing his best to stay glued to that thing. So this is essentially how an aim constraint works. And if we don't provide an orthogonal matrix, if I don't do the second cross product, you're going to see that he starts getting real weird because we're no longer providing an orthogonal matrix. And so he's actually getting scaled. And if we move this control around, he's going to get scaled in increasingly strange ways. The closer that the n and up vectors are to each other when we build this. So that's why we do that extra cross product to make sure that all of the vectors that we're describing are orthogonal to each other. That's very important if you don't want to skew something. Okay, with that, let's go to the next example. So this is a pretty similar setup. We're just going to do the copy to points and we're going to aim based on that control. But rather than having to make this matrix from scratch every single time, it's much simpler to just use something like there's Vex functions that are built to do this for you. So again, let's get the target position. So vector target is 0.1p0 because this is the same setup. We're just grabbing the position of this little cross here. I'm going to say the aim vector is equal to, again, normalize it. I'm going to subtract p from the target position. So we're getting the vector that aims the pig head at the cross. I'm going to get an up vector again. And for this, just be arbitrary, define 0, 1, 0 as our up vector. And then rather than having to do all these cross products manually, Houdini has this really great function called make transform that's going to do all of this for you. So matrix 3M is equal to make transform. And what it wants, there's a lot of different overloads to this function. You can see them in the help. But at its simplest, what it wants is an aim vector and an up vector. So aim up. And then again, I'm just going to bind this resulting matrix to 3 at transform. And now copy to points reads that transform attribute. And I can, again, move this controller around. And it's doing, I've got this wrong one templated here. I should turn that off. It's going to get confusing. But now I can move this around. And again, Houdini is basically doing all of those cross products to get you an orthogonal matrix under the hood for you. So you don't have to spell it out completely. But make transform is essentially doing exactly what we just did. The other thing that we can do, and there's a lot of different ways to solve these problems, like there always are in Houdini, rather than go through all of the effort of even figuring out an up vector and all this other stuff, we can just say we want this target vector and then just say matrix 3M equals look at, and we just give it the target point and the starting position, like what vector are we starting from to look at, bind that to a matrix, and it's going to do exactly the same thing. So you can grab this control, wiggle it around, and it's doing exactly the same thing. So Vex gives you a ton of tools to do this so that you don't have to think quite so hard about the math. But it is important to understand conceptually what you're actually building when you build a transform matrix. You want an orthogonal stack of 3 vectors. That's the basic 3x3 transform. Okay, let's keep going. So another thing that you can do in, and this is something specific to Houdini, and I'll explain in a little bit more detail why this is the case later. And this is something they actually added pretty recently. Houdini allows you to blend between 2 matrices by using the slurp function. Normally, slurping is something that you can only do between quaternions, which we're going to go over at the end of this whole section. But Houdini kind of gives you this little shortcut so that you can quickly blend between matrices and not have to worry so much about going into quaternion land, because it takes up extra lines of code, and quaternions are really confusing. So what I'm going to do is, this is again the same setup that we're just sort of layering on over and over again. I'm going to grab the target, bind it to a vector. I'm going to make that aim matrix that we just made using the look at function. So look at target from position P. And then I'm going to create a third matrix that's just going to be, let's say I want just a blend to decide how much do I want to have this pig head look at this object. So I'm going to say matrix 3, we'll call this ID, or the identity matrix, and then set it equal to ident. Ident is a function that generates the identity matrix. And if you remember from early on when we were talking about that, when we looked at that matrix toy, the identity matrix is just ones diagonally across the board. And it just means that X is X, Y is Y, Z is Z. So we're essentially saying no operation. Now what I'm going to do is determine a bias value. So this is going to be basically the blend factor. In MOPs terms, this would be the fall off. So here's my bias factor. And then what I'm going to do is say M, this matrix that I want to output, is going to be slurp, which is basically blending orientations. I'm going to say blend between the identity matrix, so no operation, and our aimed version of this. And I'm going to blend it using that bias value, which is sort of a 0, 1 value, where 0 is going to be the identity matrix and 1 is going to be our aimed matrix. And now when I do this and I go here, if I grab this control, sorry, I just need to, oh, I forgot to bind it to transform. So 3 at transform equals M, and now copy to points is reading it. Or should be. Let's make sure I'm looking at the right. There we go. So now when I drag this slider, let me template this. I can move this thing around and it's going to be looking at it and aiming the same way it was before. Let's sort of crank him up a little bit. But now when I go to this wrangle and I adjust this bias, I'm interpolating between those two matrices, right? So I can blend between them. This is effectively what fall off is doing for a lot of operations. It's just taking these matrices or quaternions or whatever they are and interpolating between them based on a bias. This is applying the same bias to every point, but in MOPs, what it's letting you do is read a point attribute, the MOPs fall off attribute, and apply this bias individually to every single point as you do these blends. So now let's go to this next section, aim without up. And what I want to talk about here is sort of related to a very common problem that happens in Houdini when people are trying to orient things, but they don't understand these fundamental terms that we've been going over here. So in this first copy to points here, all the way on the left, I have this pig head here, and the pig head is facing positive Z by convention. Up is up, Z is forward. And now I have a grid and I've computed normals on it. And you can see that the normals are all facing straight up. When I copy this pig head to these points, why are they facing this way, right? Like you would expect that if I'm, everything is basically, air quotes normal. I've got this grid, it's facing straight up. Why are these pigs laying on their backs? Why is that happening? What's happening is that Houdini is trying to guess internally because you're only giving it an N attribute. It has no up vector. And so what it's doing is trying to guess at what that means. Like what's up? It has no idea. And so what it's doing is trying to take an educated guess. So again, if I go down to this vector visualizer here, I'm going to turn off my actual vector thing. The up vector here is positive Y. The normal vector here is positive Y, which is also conventionally what you would think of as the up vector. They're completely perpendicular. Completely parallel. So Houdini is trying to guess which way up should be by creating an identity matrix and then rotating that matrix so that its N lines up with yours. Let me just turn on another visualizer here. So you can see that if Z, instead of facing Z this way, is facing up, then what it's doing is saying, well, up must be facing back here towards negative Z. It's rotating the whole thing because it needs an orthogonal matrix in order to work. And you're giving it a normal vector that by definition requires it to be facing this other direction. It doesn't know what to do. Let's go over here to visualizer 3. So the guess that it's computing is based on the same vector math and trig that we were doing before. So it's looking at your old normal, like sort of the default world normal, which is 0, 0, 1. It's then saying, okay, your new normal is 0, 1, 0, right? Like that's the normals of the grid. And it's saying, it's trying to figure out the axis of rotation between them. So this is step 1. how do I get the world forward vector, positive z, to be facing positive y, which is what we've told Houdini to do. So it's crossing those two vectors together and then getting you this red axis here, which is the x-axis. So that's step one. The next thing that it's doing is, and I'm just going to turn on this visualizer here so that we can see what's going on, is, and you can see that this is sort of returning the identity matrix right now. X is X, Y is Y, Z is Z. What we're going to do is do a little bit of trig to get the angle and the axis to rotate positive Z onto positive Y. So bear with me here. There's a little bit of code involved in this. I'm going to describe my old normal vector. So this is, let's say, this is the world normal, essentially. This is our original case is 0, 0, 1. We know this already. Our new normal, where we want to get to, is 0, 1, 0, because if you remember that, what we were looking at earlier, our grid normals are facing positive Y. So as we know, if we want to find the axis of rotation between these two vectors, we can use the cross product to do it. So I'm going to say our axis is equal to the cross product between old n and new n. This axis is effectively going to be x or negative x, depending on the order in which we define the cross product. So the next thing that I need to do is find the angle between the two vectors. And before, if you remember, we can invert the cosine function and use that on the dot product, the ratio between the two vectors, to find the angle between them. So float angle is equal to the arc cosine, acos, of the dot product of old n and new n. So this is going to give us the angle between these two vectors in radians, which is going to be pi over 4, essentially. We already know this. Now that I have the axis and the angle, what I'm going to do is create an identity matrix. I'm just going to create a generic matrix here and then rotate this matrix. And rotate is a special Vex function that, if you didn't already know this, when you look at Vex functions, there's a handful of them, including rotate, scale, XYZ dist is also a really common one, that if you look at the documentation and you see an ampersand here in your parameters, what this means is it's an out type argument of a function. And what that means is that rather than just return, whatever is on the left here, like normally you'd say like float or matrix 3 or vector, where like the function returns something. So you could say this equals this. An out type argument with this ampersand means that it's going to write directly to those values in the function. So I'm not actually returning a value here. I'm just overwriting the matrix definition by using the rotate on it. So the first argument here, m, is the matrix, and this function is going to write directly over that value that I put in. This can get really confusing to people who aren't used to Vex. But if you look at XYZ dist, it's one of the more common functions that you use in Vex to figure out sort of the closest position on a surface. And it will do the same thing, because the closest position on the surface with XYZ dist is it's determined by two completely separate values, the primitive number that you're closest to and the parametric UV coordinates on that primitive. And so a lot of functions that write to multiple things like that are going to have these output style parameters. So look for that ampersand when you're looking through the Vex docs. Anyways, I'm going to rotate this matrix M. I'm going to rotate it by the angle that we found earlier in radians, and I'm going to rotate it around that axis. And now I'm going to bind this resulting matrix to 3 at transform so that the point wrangle can see it. And now you can see that immediately when I do that, when the visualizer that I have set here is showing now that Z is facing posit up and Y is facing towards negative Z. So, and now if I go to the copy to points here, you can see that all the pig heads here are laying on their sides. And this is why. It's, again, Houdini really needs an orthogonal matrix to make all of this work. And if you only give it one vector, if you're not providing an explicit up vector when you're trying to aim something, Houdini is going to take its best guess. And this is how it does it in order to make sure that when you're copying things, it's at least consistent from scene to scene, even if it's very rarely what you actually want it to do. So last example here, I'm going to go over to the copy points here, and I've got this whole group of pig heads. And what I want to do is just really quickly sort of show the shortcut to all of this, like this whole axis angle arc cosine thing that we just did. There's a much simpler function that you can use to figure out how to rotate one vector onto another, which is what Houdini and copy to points wants to do. So I'm going to grab old n, which is, again, z, and then the new n, which I know is positive y. And then rather than do all this arc cosine wizardry, I'm going to say matrix 3m is equal to dihedral, which is a really magical little Vex function, old n, new n. What dihedral does is it computes the matrix that would rotate vector A onto vector B, which is exactly what we just did using the cross product and arc cosine of the dot product earlier. It's just wrapping all of that up into one very convenient function for you, so you don't have to do all this by yourself. Now I'm going to say 3 transform equals m. And now you can see copy to points leans all these guys on their sides exactly like we would expect. So this is something that I think every beginner to Houdini gets tripped up on if they don't already know how this stuff works under the hood. Houdini needs an orthogonal matrix and to describe any kind of orientation or transform in space. And the way that it's going to compute that is by doing this math under the hood. So it's going to, if you're not explicitly telling it what up is, it's going to take its best guess. Let's keep going then. Now let's talk about accumulating matrices. Just again, head all the way over to the left here. And then I've got this quick little example written up here. Let's zoom in here. So what I'm doing is I have an axis and an angle, and I'm doing this twice. So I'm defining a 90-degree rotation around the y-axis, and then I'm defining a 90-degree rotation around the z-axis. And I'm applying both rotations to this matrix, and then multiplying that point position against matrix A and then matrix B. So you can see that this thing is rotating around y first. Here, I'll just disable this temporarily. So it's if I don't do either of these rotations, it's facing this way by default, like we'd expect. So here's that 90-degree rotation that we're applying. And now here's the 90-degree rotation around the z-axis. So now he's facing up, he's on his back again. If I reverse these two terms, so if instead of p times a times b, I do b times a, I'm changing the order of operations. So and you'll have this apply to Euler rotations as well if you like to define things there. That this is why you have to say what rotate order you want. If you're defining things in terms of like, I want to rotate 30 degrees around x, 60 degrees around y, 90 degrees around z. That's why rotate order matters. So the order in which you multiply transforms together is going to determine the order of operations. It's going to determine it's going to affect the result of what you're kicking out as your final transform. So now, rather than just multiply P against matrices, let's start actually messing with packed transforms, because this is when you're dealing with copy to points and things like that. A lot of the time when you're defining these transforms, you're sort of tweaking the intrinsics under the hood. This is what MOPs does as well. So I'm going to start with this pig head and then just run MOPs convert. And this is just a fancy, you could do this with a pack stop. It doesn't matter. MOPs convert is just convenient. And then I'm going to use a transform modifier to rotate this guy 4 to 5 degrees around X. And I still have my spreadsheet open showing the packed intrinsic, but you can see that it's all the vectors have been slightly adjusted. So this rotation has been applied. What I want to do with this is sort of explain the difference between a local space rotation and a world space rotation, because it's simpler than it sounds. But this is going to be a lot of Vex, so apologies. What I'm going to do first is I'm going to grab the intrinsic transform that we've just defined on this. So the transform intrinsic, at least the one that we're going to be dealing with, is a matrix 3. So it's describing orientation and scale. The translate part of this is just defined by at P, right? Because with packed primitives, the position we still have accessible to us as a vector attribute. You can get the full 4x4 matrix if you want to, but we'll worry about that later. So matrix 3A is equal to prim intrinsic is the function that you use to fetch intrinsic attributes about something. And I'm going to grab them from input 0 because I'm just working on myself. And then the name of the intrinsic is transform. I'm going to fetch it from the current point number. Primitive intrinsics are fetching attributes from primitives and not points. But because the sort order here, because my point sort order is the same as my primitive sort order, I don't have to differentiate between the two, which is why I'm using ptnum. So now what I'm going to do is make a second matrix, and this is going to describe the rotation that I want to apply to this packed primitive. So we'll start from an identity matrix. I'm going to call this B, and it's just ident. So currently it's applying no transformation at all. I'm going to define an angle. So we're going to say float angle equals radians, and then let's make a parameter for this so we can kind of play around with it. So I'm going to make a float channel called angle. We're going to specify it in degrees, and then we're converting it to radians for the purposes of rotation. Most Vex functions in Houdini, unlike HScript expressions, most Vex functions want radians. HScript, if you're using like sine functions or anything like that, they usually want you to talk about things in terms of degrees. But Vex wants you to approach this like a mathematician. They want you to use radians. So keep that in mind. You have degrees and radians functions to do those conversions for you. Because most artists are going to want, if you were parameterizing something like this and presenting it to an artist, they're going to want to think in degrees. They're not going to want to think in radians. But just keep these conversion functions in mind. They'll come in handy. The other thing to describe a rotation that I need is also an axis. So I'm going to say vector axis is equal to, let's just bind this to, we want to rotate around world up. So we're going to rotate around the y-axis. And now I'm going to apply that rotation. So rotate B by that angle around that axis. So now I have my original transform and I have my B transform. To make this easier to look at, I'm going to create a third matrix, and this is going to be our output. So I'm going to say matrix 3 out, and then just not define it as anything because I'm going to write to it in a second. What I'm going to do is make a toggle on here that says whether I want to rotate in world space or not. So yeah, again, pardon all the Vex, but what I'm going to say is if, and I'm making an integer channel here called world space. This is effectively a toggle. So if this toggle I'm about to make is 1 and not 0, then I'm going to rotate in world space. So out is going to be equal to A times B. Otherwise, out is going to be equal to B times A. Okay, and now that I have this output matrix, I need to write it back to the intrinsic. So set prim intrinsic is the function to use for this. I'm going to say 0. Transform, again, is the name of the intrinsic. I want to write to the current transform intrinsic associated with this point number. And then the value that I'm writing is out, this matrix that I just made. Once I do this, and then hit this button to define these terms. So I've got this world space toggle here at the bottom, and then I've got this angle. And let's, I'm just going to type an expression in here and just say frame times 5. So every frame, it's going to rotate 5 degrees. So with world space off, I'm rotating, when I'm building up this matrix, I'm starting with matrix A, which is the current transform, and then I'm multiplying it against the rotation around Y. So this axis here, that rotation is happening after the fact. So if I scrub the timeline, you can see that he's not rotating around Y, he's rotating around what he thinks is Y. So if you look at the pig head here in the right camera, he's rotating around his own local idea of what Y is. But if I enable world space here, so if I just set this to some non-zero value, and now it's B times A, I'm applying that rotation around Y first, and then I'm applying the local rotation or the local angle that he already had, that sort of tilt in 45 degrees that we described earlier. And now you can see that he's rotating around world Y. So when you're thinking about something happening in local space versus world space, it's really just about the order of operations. It's about like, are we considering his own local rotation first and then applying this new matrix? Because that, when you multiply matrices together, you accumulate all of these different transforms all you got to do is just decide, well, do I want to do this rotation first, or do I want to do it second? That's it. So it took me a while to wrap my head around it until I sort of had to break it all down and spell it out for myself while writing some of these operations in MOPs. But it's literally just, is it A times B or B times A? What order of operations are you applying this rotation in? And let's go to one other example here. So here I've got basically the same setup. What I'm doing on this one instead is in the transform modifier, I'm rotating around the x-axis over time. And what I want to do is just sort of show how scaling works with this as well, because the rules are very similar. So I'm actually just going to copy most of this code because it's primarily the same. But what I'm going to do for these matrices is going to be a little bit different. So instead of defining an angle and an axis, I'm just going to say vector scale is equal to, and I'm just going to make an arbitrary scale vector. And then I'm going to take this B matrix, which again is just the identity right now. I'm going to scale B by this scale vector that I've just put out. Everything else is the same, because with matrices, the magic of them is that you just define what these numbers are and multiply them together, and then you accumulate transforms. So when I click this, I'm just going to set my scale to 1 to start, and then view this. And so right now it's just doing what it was doing before. But let's say I want to scale along Y. So on the first frame where I have no rotation applied, you can see that he's stretched out vertically. It's probably easier to see here as well. And if I just spin the timeline, you can see that he's stretched out consistently along his own local conception of what Y is. But if I reverse the terms of the matrix, now he's going to start stretching. And it might be hard to see in the screen, but you can see he's no longer stretching along his own axis. He's kind of morphing as he rotates, because we've reversed the terms. We're applying the scale first and then we're rotating instead, or we're applying the rotation first and then scaling. And that affects the outcome pretty considerably. Okay, so the next thing that I want to talk about, and this is where things are going to get a little hairy, is we're going to start introducing 4x4 matrices here and start talking about translation. So we've been dealing so far with very simple, well, comparatively simple 3x3 matrices, which just describe scale and rotation. But in computer graphics, regardless of the interface that Houdini gives us to describe these things, in computer graphics, you're generally dealing with a 4x4 matrix, which describes translate, rotate, and scale. So we're adding position into the mix. The reason why it's 4x4 is essentially just for a lazy math shortcut. Matrices are a lot easier to multiply together when they're square. And if you remember, we had 3 vectors that were describing our position orientation, just x equals x, y equals y, z equals z. Now we want to offset that. And so we need a 4th vector. But if we just layered that on, we would have a 3x4 matrix, and it's really annoying to multiply matrices together when they're lopsided. So the solution of a 4x4 matrix, and you can see it here if you look at this first matrix 4 toy, it looks pretty familiar, right? We have 1, 1, oops, I don't know how that happened. We have 1, 1, 1 going down diagonally. And then we just have this extra 3 set of numbers at the bottom here, and then a bunch of zeros that are added on. And these are, for most purposes, you can just completely ignore them. They're just there to take up space, but they make the math a lot easier to handle under the hood. One other thing I should mention is that the order in which you're seeing these values here is what we call row centric. So row 1 here is our x vector, row 2 is our y vector, row 3 is our z vector, and row 4 is translate. A lot of the time, if you're looking at math online or in math textbooks or in other software, you'll see matrices described as column centric. And it's basically taking all of this stuff and rotating it 90 degrees. So X would be instead this first column, Y would be the second column, Z would be the third column, and translate would be the last column. This can get confusing if you're trying to translate this to directly what you're seeing in Houdini. It's really just a convention of like how you want to store the data. And there's some like memory management angles to it. Like when you're building up arrays of vectors, sometimes it's easier to read them one way. Sometimes it's easier to read them another way. Just keep in mind that Houdini is row-centric, and a lot of other matrix descriptions, like if you're looking up any of these operations on Wikipedia, they're probably going to describe them as column-centric. It's a big point of confusion. Just be aware of it because you'll have to sort of transcribe this in your head when you're doing all this stuff. Anyways, a 4x4 matrix largely works the same way. If I stretch out 1 here, he's going to scale along Z. Same with Y, same with Z. And if I scale along multiple vectors, he'll start skewing. These numbers down here are the translates. So I can move him along X here. I can move him along Z here. And I have like this quick expression to just make him move up and down in Y using a sine function. So real simple here. We're not doing anything magic yet. Now let's start multiplying these matrices together. So what I'm doing here is I'm, again, starting with this CH4 is sort of the shortcut for describing a matrix as a single parameter. So that's where this is coming from. And then I'm making a B matrix, again, starting from identity. And then I want to rotate it. So I have an axis and an angle here. I'm rotating 90 degrees around Z. And then I'm going to rotate this object around that axis. So here's my start point, looking like this, zoom in. And here's my endpoint. If I switch these, and sorry, before switching the terms, I want you to just look at this and scrub the timeline a bit. And you can see that because I'm starting with A as my matrix order, when I move this guy back and forth, even though I'm translating along Y, the translation is applying to local Y because I'm multiplying A first and then B. So you can see that really he's moving along the x-axis, but it's his own local idea of what Y is. If I switch these terms, so I'm doing B times A, now he's going to be facing sideways the same way he was before, but the translation is going to be applied in world space. It's going to be applied in the terms of this second matrix or this first matrix here rather than the second. So the rules for 4x4 matrices are largely the same. We're just adding some extra numbers to it. Okay. Another thing that you can do with matrices that's really fun that you should know about is you can invert them. And inverting a matrix is basically an undo. So I have this quick matrix parameter that's already sort of built for you. And all I'm going to do is just say, I accidentally deleted this parameter, but I'm going to say matrix A is equal to CH4 matrix. So that's going to bind directly to this parameter that we just defined. And then I'm going to multiply P by this matrix A that we just defined. And then the last thing that I want to do is I want to save this transform as it is to an attribute that we can read later. And a 4x4 transform, as opposed to a 3x3, is in Vex, if you want to bind that to a parameter, you use the prefix 4. So 4 at x form is equal to A. And so if I look in my spreadsheet under points here, you can see I've got this very long x form attribute that's 16 digits, 4x4 matrix. So I've bound this to something. And because I'm multiplying P by A here, it's the same as any other matrix. And I multiply these together, P goes up, P goes down. Now let's undo this. So what I can do, this is the reason why I saved this attribute to, or I saved this matrix to an attribute, is in the second wrangle down here, I can undo this operation. So I'm going to say multiply P again by invert and the name of that X form attribute that I just saved out. And when I apply this transformation and scrub the timeline, nothing happens. Sorry, Tom, does the ident for an M4 have a 1 in the lower right? Yeah, the 1 in the lower right is, yeah, I think it depends on exactly the coordinate system, and feel free to correct me if I'm wrong here, but it largely doesn't matter. A lot of the time, so that you have like a true orthogonal like determinant on a matrix or whatever, like you'll see a 1 down there. In most situations, it doesn't seem to matter that much. But a lot of the time when you see these set up like in other 3D software, there'll be a 1 down there. But for what we're doing, it's not really going to affect anything. Does that help? So it's possible. You wouldn't normally describe direction using a 4x4 matrix like this, although it is embedded in there. So, but yeah, I think in most CG software that I've seen, you would typically end up having a 1 down there just to keep this orthogonal. But for what we're doing, you can see that if I set it to 0 or 1, it really doesn't. It's not affecting the result considerably for what we're doing. You know, I can change it, and it's not doing anything. I think for safety reasons, it would usually be 1, but I would defer to Divi's class because he knows matrices, like the underlying concepts of it from math terms. He probably knows them better than me. Okay, yeah. So going back to this, the nice thing about inverting matrices, not only is it as an undo step, but what it allows us to do is we don't have to invert our own matrix. We can invert someone else's matrix and apply it to ourselves. And what that allows us to do is if we multiply a matrix, our matrix, by the inverse of someone else's, we can sort of move ourselves into their space, which is really useful for things like parenting operations, where we want something to move as if it's tied to something else. Having that inverse matrix there sort of gives us the power to space switch. It gives us the power to move into other more useful coordinate spaces, do an operation there, and then potentially move back if we need to. Before we go further into that, what I want to do is describe how pivots work. There is a pivot intrinsic in packed primitives, and it largely means the same thing as what we're about to deal with here. So what I've got is a pig head, and I'm just moving it 5 units away from the origin, right? And now what I want to do is, let's just do the same rotation that we've always been doing to these things. So I'm going to create a matrix. All right, let's make it a full matrix instead of a matrix 3. Call it the identity matrix. I am going to describe an angle. So let's just say radians. We're going to take the sine of time and rotate by, so we're going to rotate back and forth by 45 degrees. That's all. So 45, negative 45, just bouncing back and forth. And we're going to rotate around the x-axis. So again, to apply this rotation to the matrix that we've just built, we use the rotate function. So I'm going to rotate m by angle around axis. And then as the last step, I'm going to multiply p by this new matrix that I built. And when I run this rotation, you can see that he's not rotating locally, he's rotating still around the origin. Because when we do these matrix operations, unless we say otherwise, everything is based around the origin, which is effectively our parent space. So we're not just getting rotation now, we're getting, you know, these points are translating around as well as just rotating around their own local origin, right? It's a very different move than if we, you know, let's go up here to this peak and then move this transform back. And you can see that he's translating back to the origin. So this is effectively how pivots work. If we want this pig head to rotate around his own local origin, even though he's off here out in space somewhere, we need to make that adjustment. So if you go over here to this next example, pivot adjust, what we're going to do is we're going to make that adjustment before we do this matrix operation in order to make sure that he rotates around his own local space. So I'm going to go back here to pivot intro here and just copy these first 3 lines so we don't have to type that again. So the rotation is going to be the same. We're going to bounce back and forth by 45 degrees. What I want to do next is I want to find the pivot point that I want to rotate around. And in this case, I want this to basically be rotating around the center point of the pig. I could just take the value of this translation and say like, oh, I want the pivot to be 005. But let's say that that's not an easy thing to fetch and I don't want to bother pulling in that data. I'm going to define the pivot as being the centroid of the bounding box of this pig. And there's a very handy Vex function for that called get bbox center. And then I'm just getting the center of whatever SOP geometry is in input 0. So now I have a vector that's pointing to the exact centroid of this pig head. And now again, I'm going to take this matrix that I built, say rotate m by angle around axis. And now before I multiply p by this matrix that I've built, what I need to do is offset everything so that the pivot point is at the origin. To do that, I'm going to subtract vectors. So I'm going to say p minus equals pivot. So I'm subtracting 5, which is that pivot point, from every point here, which is effectively going to move that pig head so that its centroid is at the origin. Then I'm going to multiply all points by that matrix to apply that rotation. And then after that, I'm going to add that pivot vector back in world space so that he goes back to his original position. And when I do that and then scrub, you can see that now he's rotating around his own local centroid. And this is basically how pivots are working under the hood. It's like giving you an offset so that you move that pivot point to the origin, because matrix operations like this are always going to have relative to whatever your parent space is, right? And in SOPs, you don't really have parent-child relationships unless you're using kin effects. Like everything is just sort of happening in the space of the object container that you're in. So if you want to be doing these kinds of pivoting operations on SOPs where you don't explicitly have parent spaces defined, you need to make these changes yourself before you're multiplying anything against a matrix. Mm-hmm. Yes, but the slippery part about RBDs is that the pivot changes over time. With every collision, it will update the pivot point. And a lot of the time in the first frame of simulation, it's going to shift the pivots of every RBD chunk to match the center of mass, unless you disable that in the solver. And so that can kind of complicate things. And it's also, it's depending on how you're reading the data from the RBD sim, you could either be using the pivot intrinsic. If you're like fetching packed primitive data, like you just basically pass through packed primitive data, it's going to write all of this to the pivot intrinsic. And that pivot intrinsic, the offset that it describes is in local space. So the pivot that it's giving you, and if you want code examples of what this looks like, crack open MOPs pivot, because MOPs pivot is doing all of the same math under the hood to figure out pivot orientations. But if you describe a pivot point as an intrinsic for Houdini of like 1, 0, 0, so you're like offset by 1 and X, that offset by 1 and X is in the local space of the transform, not in world space. So you have to, if you're trying to shuffle the pivot around in world space, you need to first take that pivot vector and multiply it by, I think, the inverse transform matrix of the packed primitive, then do your changes, and then probably multiply back by the original matrix again before you reassign that intrinsic. It's very confusing. Yeah, I couldn't even quote the math for you off the top of my head because it is really confusing to do. I would MOPs pivot has all of that stuff built in, and you can kind of see how it differentiates all those operations based on whether it's solving it in local or world space. Okay, so I'm going to do one more really hideous example here, and I apologize for all of the Vex, but I kind of want to describe how you would define a parenting-like relationship just using SOP geometry. So this is something that KinFX sort of does for you. It still can be confusing to work with because KinFX is still a little new. But what I'm going to do is basically describe forward kinematics to you. Forward kinematics is a series of transforms. And this also applies to like a typical object hierarchy. Like if you're in OBJ context in Houdini, or if you're looking at something like the outliner in Maya or whatever the equivalent is in C4D, where you have like a tree view where objects have parents and children. The concept behind it is essentially accumulating transformation matrices over time from parent to child. This is going to be a lot of Vex, and I apologize for it, but bear with me here and feel free to ask questions if you get stuck, just chime in. So what I'm going to do is essentially I'm going to take all 5 of these pig heads in a row, and I'm going to rotate each one of them locally by about 5 degrees. But I'm going to treat it as if this is a joint chain where this pig head all the way on the left is the root. And then each one of those is parented to the one before it. And they're all going to get rotated by about 5 degrees. So what we should end up with is sort of like a bendy line. Like if you can imagine selecting all the joints in a chain and rotating them all at the same time, they'll start curling up. And that's what we're going to do here. So float angle is equal to, again, I'm just going to build an angle axis matrix. I'm going to do this based on a parameter. So I'm going to define an angle in degrees as an argument, and then I'm going to define an axis. And I'll do both of these as parameters just to start. And if I click this button, I get them both at the bottom here. And just to have this ready to go, I'm going to have these guys rotating around X so that they're all bending perpendicular to the way that they're facing. And let's just have let's have the angle be the sine of the current frame. And let's speed it up. So we're going to multiply frame by 4 so we get a faster movement. And then I'm going to, how about instead of 5 degrees, let's rotate a little bit further. Let's set it to 20. So the frame multiplied by 4 is going to increase the speed at which the sine wave evaluates. So we'll get a faster bounce. And then I'm multiplying by 20. So we're going to rotate each joint by a minimum maximum of 20 degrees. And everything's going to be rotated around the x-axis. Okay, so just give me 1 second here. Let's start coding. So what you need to do in order to get a parent-child relationship to work is for each object in this chain, and notice that this is a detail wrangle. We're not iterating over points at a point wrangle for this. And the reason we're doing that is because order matters. When you're doing a parent-child relationship, we want to solve the parent's transform first, and then carry that transformation matrix over and over and over again down the chain. That is how forward kinematics works. So you can't solve it in parallel the way that you'd like to, where you're like evaluating all points at once. You need to solve the root first, and then carry that transform down the chain. And what that means is that we're going to solve this as a detail wrangle, and we're going to use a for loop to iterate over every point in order. Because if you use this as a point wrangle, point wrangles run, they're threaded, they run in parallel. You have no control over who goes first. So just trying to explain why that's happening there. And before we go into that loop, what we want to do is define sort of our starting transform, like who's first. And to get that transform, I'm going to say matrix parent x form. You can call this whatever you want. This is a local variable, but I'm calling it this for visibility. And rather than grab the, there is an intrinsic. If you go in the list here for packed primitives, sorry, I have to go back to copy to points here. Aside from just the transform intrinsic, which is a 3x3, there's another one called packed full transform. And this is the full 4x4 transform matrix for each one of these things. You can, in Vex, fetch that by using the same prim intrinsic function we used before, but there's a shortcut that they added sometime around Houdini 18 maybe called get packed transform. And I'm getting it from input 0, so the first input here, and the primitive number I want to get is the first pig, so 0.0. So now I have the transform matrix of this first pig stored as this value. And the second thing that I want to do is get the pivot point, right? Because there's a parent-child relationship here, and I want each of these things to be rotating relative to its parent. It's going to be rotating locally, but the transformation, it needs to be happening from its parent position. So I'm going to store the current pivot or the initial pivot as the position of that point. I could also, if I wanted to, I could pull P out of this transform matrix if I had to, instead of fetching it as a separate attribute, but it's just way more convenient to get it as P. And I'll explain more about how to sort of pull information out of matrices in a second. So now what I need to do is I need to iterate over each point in order to get its transform matrix and apply this rotation. So to do that, I'm going to use a for loop. I'm going to start int I is sort of our if you're not used to for loops in Vex, I is our iterator. What we're doing is we're saying, let's start counting, and we're just going to write to this variable I in our counter. We're going to start with it at 0, and we're going to end when we reach, if we say I is less than the number of points, we're saying just like end when we hit the last point, like stop the loop. And then this third term just means I goes up by 1 for each count. So all we're doing is we're counting over and over again, and the value of I is increasing from 0 to 4, essentially, which is the index of the last point. So now what we're going to do is build this transform. This is the transform that we're going to be applying locally to each one of these pig heads. So matrix B is equal to the identity matrix. And let's rotate it. So we're going to rotate B by angle around axis. And again, that's going to be this sort of sine wave function that we've generated down here. And now what I want to do is, so again, I have the parent transform set up here, but I need to get my own transform, and we're going to call that matrix A, right? So I'm going to say matrix A is equal to get packed transform. Again, I'm pulling from index 0 into the wrangle. And the primitive number that I want to get this case, because I'm talking about like my own transform for each point, is going to be number I. So I'm getting packed transform I in the loop. So the current matrix that's being affected. Now, in order to get this transform to be, because I want each of these pig heads to be rotating around, like basically the transformation needs to be applied to itself relative to the parent transform. Because if I rotate this first pig here, I want the rest of them, all the children, to also follow that rotation. And then I want the pig head itself to rotate by itself that additional 20 degrees. And that's what's going to get us that curling action. Like that's what's going to get us the FK part of this, rather than each pig head just rotating individually. So what I need to do is I need to take this pig head and I need to move it. I need to essentially subtract the pivot position of whatever the current pivot is defined to be from my current matrices position. Because we're dealing with matrices and not the P attribute here, this is a little bit more complicated, but Vex gives you functions to handle this. One function that you can use is translate, and then you can basically just pass it a matrix and then say, I want to translate it by the opposite of the pivot, because we're subtracting. So I could just say translate a negative pivot, but translate is going to apply in the wrong space. What it's going to do is it's going to consider all of the rotations that are applied to this matrix when we do the translation. And we won't want to do that. We're fetching our pivots, our point positions in world space. So this is sort of a weird distinction, but in order to get this translation to happen without the rest of the matrix interfering in that direction, what we can do is instead say pre-translate, which is a convenience function that Vex gives you to basically say, we want to do this translation before we do any other wild stuff with this matrix, before we consider anything else. There's also pre-rotate and pre-scale functions. And if you're messing around a lot with kin effects, you'll start seeing those coming in handy a lot, especially pre-rotate when you want to define rotations in local space and not end up getting like really weird results. Anyway, so what this is doing now is it's shifting each pig head back onto the previous pig head if it exists. Now what we're going to do is determine our output matrix. So matrix out, and what we're going to do is we want each pig head to be rotating, basically following any transforms that happen to its parent in its parent's space, which is why we did this pivot offset. And then we want to apply this rotation to itself. So what we're going to do is multiply by the parent transform. So we're going to apply our parent's transformations. And then we're going to apply our own transformation, so our own packed transform again, basically moving it out of its parent space after we've done the original transformation. And then we're going to apply this new rotation to itself. So for each pig head, we step back, we apply the parent's transformation, we apply our own transformation again, and then we apply the rotation. It's complicated, but I hope this makes sense. FK honestly is a complicated thing to kind of wrap your head around. It gets way worse if you're trying to understand IK. And now what we're going to do is update the packed transform now that we've computed this new one. And there's another handy shortcut function for that. You don't have to use set prim intrinsic. If you're dealing with 4x4 matrices, you can just use set packed transform. And we're going to set 0th input. We're going to set transform number I, because we're in this loop. And we're going to set the value to be out. And then before we close the loop, each parent transform, we define parent transform at the beginning, and it's transform number 0. But for each successive point, we want to get the new parent transform. So like we need to update this at the end of the loop so that the next primitive in order is reading the previous transform that we computed, because this is accumulating throughout the loop over time. So I'm going to say parent transform, parent xform is equal to out, this new matrix that we just computed. And similarly with pivot, I'm going to say the new pivot point is equal to the new position that we've just computed of point I. And now we close the loop. And if we do this, what you're going to see as you wiggle the timeline around is that each of these peg heads are translating in space as if they're being rotated by their parent and then doing their own rotation. So you get this kind of wiggly, snaky behavior as if you were rotating a joint chain. So, and if you were doing the same thing with transforms, it's not just joints, it's any kind of parent-child relationship, you would get something like this. So again, it's matrices all the way down. Everything in CG that is in vectors is going to be matrices, and it's just a lot of these fancy transforms just depends on what order you're doing them in, and parent-child relationships becomes like another order rather than just world or local space. It becomes, okay, well, we need to take this one starting transform from like the great grandparent all the way at the top of our dependency graph and move all the way down to the end of each chain. And when you do any kind of rotations or anything like that in any computer graphics program, this is what's happening under the hood. You're taking all these transforms and just accumulating them top to bottom for every leaf in your tree. Okay, so really quickly, I want to go into quaternions. I'm not going to go deep into this because quaternions are terrifying wizard math, and I don't understand them myself. I don't expect anyone else to. But I understand enough about them to use them practically and to sort of loosely describe what they're meant to do. So if you want to visually see what quaternions are, if you feel like you're ready to start looking at four-dimensional spaces, quaternions are a math trick. Basically, they're using complex numbers, which means that the imaginary number I, if you've heard of that before, basically, if you were to break down like this into a 2D graph, and let me just get my annotation tool back here, and you could say that instead of a 2D graph being X and Y, let's say that this axis is real numbers. So this is 1, 2, 3. With imaginary numbers, you've got a separate axis here, which is I. And I is a number with extremely weird properties that mathematicians kind of just made up. That is basically saying the square root of -1 is I. And so I squared is equal to -1. I think that's how it works. It's very odd. But what it means is that if you multiply I over and over again by itself, it oscillates between 1 and -1. So when you take like and again, we're simplifying this into 2 dimensions, but when you take real components, so we have like a vector, like real numbers out here, and you multiply them over and over again by I, and these are complex like polynomial equations, so there's more to it than that. But basically, you get this oscillation going up and down in the imaginary number plane. And if you have real coefficients to those numbers, you basically start getting circles. So quaternions are doing a lot more than this, but essentially what you're getting is a really cheesy way of being able to take a 3-dimensional vector, right, that's describing like a rotation, and break it down in a mathematically convenient way to be able to describe and also interpolate between rotations. And you're only using 4 terms because a quaternion is a 4-dimensional vector. It's wizardry. I mean, quaternions are amazing, but I am not qualified at all to understand them. But it's just a really cool math trick that makes it mathematically fairly simple, at least in computing terms, to describe an orientation as 4 terms instead of 9. And as part of that process, it makes it very easy to be able to blend between them. And that blending is what we did earlier with matrices called slurp. But that's Houdini kind of making our lives a little too easy. You cannot actually spherically linearly interpolate matrices. Houdini is converting them under the hood for you and doing all of the quaternion math and then converting them back. So the reason why it's important to know sort of at least what quaternions can do is because they are everywhere. Any game engine that you've ever used when you're like, if you've ever tried like programming some simple stuff in Unity or whatever, where you're like rotating your little guy around on the screen to like move towards a direction or something, it's all quaternions under the hood. And the reason for that is because quaternions blend really easily without flipping. If you've ever, any of you who've been character animators who have set keyframes where you're trying to set Euler rotations and blend between them, you're in the graph editor or whatever, trying to adjust like your rotate X 90 and rotate Y this and rotate Z this. And all of a sudden, like stuff gets locked up and starts jittering and flipping and all of that. That's called gimbal lock. And it's an intrinsic problem with any animation in 3D because most animators, any animator can't really think in quaternions. They're thinking in Euler angles because just conceptually quaternions are insane. But under the hood, all of these engines, when you're telling these things like, hey, slowly aim this thing at this other thing because I want my tank to be shooting in this direction instead of this one, it's going to be quaternions under the hood. That's what it's working with every time, pretty much without fail. What I'm going to do really quickly is I'm going to take this pig head, and first I'm going to clear all this garbage off my screen. And what I'm going to do is just build a little thing that will rotate between two different orientations and blend between them. So first I'm going to create my initial like rotation A. So like my default orientation. I'm going to call this ROT1. And this, I'm going to basically make this identity, but the ident function returns a matrix, the identity matrix like we were doing before. But what you can do with a matrix is you can wrap it up as a quaternion using literally the quaternion function. So in Vex, you can say, take this 3x3 matrix, and there's other overloads to this function. You can define a quaternion out of an angle and an axis as well. But in this case, I'm taking this matrix and saying, okay, you are now a quaternion. But it means the same thing. A quaternion defines an orientation similarly to what a 3x3 matrix does. So this is a ROT1 is a no op quaternion. It means nothing. The second one, ROT2, what I'm going to do is basically, I'm going to run the random function. So I'm just going to say rand, and we'll just say seed. I haven't defined seed yet, but we'll get there. And I'm going to, didn't mean to put that first equal sign in there. And I'm going to normalize this because I want my quaternion to be a unit quaternion. The random function, in addition to creating random floats, it can also create random quaternions. So this is just going to create a random orientation for us. And then for seed, I'm just going to up here say float seed equals, we'll just bind that to a channel. And now our output. So again, I'm going to create another vector 4. I'll call this out. And what I'm going to do is use, again, slurp, which is short for spherical linear interpolation. And it's basically slurping two quaternions creates it finds the shortest path between them and blends between them. And it will do that basically every time. That's part of the magic, is that it always finds the shortest path between 2 points on a sphere or two orientations. So I'm going to slurp from the identity rotation to the random rotation. You're going to do so based on a bias channel, which is just going to be a 0 to 1 channel. So let me just hit the button here. And now I've got a random seed, which currently does nothing, and a bias, which currently does nothing. So what I need to do now is actually, rather than multiply P by a matrix, if you want this quaternion to affect the orientation of a vector, and P is a vector, what I can do is say P equals Q rotate. Q rotate rotates a vector by a quaternion, and P is a vector. So this is functionally similar to multiplying by a matrix. I'm going to say rotate out, or rotate using out. That's our quaternion, and apply this to P. And if I put the display flag on here, you can see that nothing happens yet. But if I increase the bias, it's going to slowly twist towards whatever this random orientation is that I have. And if I randomize the seed here, you can see it's just generating all of these different random orientations. But when I drag the bias down, it's always finding the shortest path between that default orientation and this new one, no matter what. I can leave it down here, and you can see it just kind of jitters a little bit. But it's always finding the quickest path the quickest path between orientations and blending between them. Let's go to the next example. So one of the other cool things that you can do with quaternions is that they can be easily initialized as an axis and an angle. So let's just code this again from scratch. It won't take long. So again, I'm going to define an angle. We did this a lot with our matrices, but this is another nice way to think about quaternions. So here's my angle, and then I'm going to define an axis. So this is going to be, I'm going to give it a normalized axis. Again, anytime you're dealing with rotations or orientations, you want your stuff to be normalized. So now I've got an angle and an axis parameter, and let's set these to, let's do like a 180 rotation around Z. And now I'm going to define my initial rotation, which again, let's just say that it's no rotation at all. So just convert the identity matrix into a quaternion. And then let's say for rotate 2, I'm going to do this, the same quaternion function, but you can see that there's a lot of overloads, right? One of them is giving it a matrix 3, which is what we were doing before, but we can also provide it an angle and an axis. So what I'm going to do is say, let's do the radians. Let's convert our 180-degree angle to radians. That's our angle. And then the axis we already defined. And then again, I'm going to say, oh, I'm sorry, you know what? These are vector 4s. Got to be careful about that. And then the out vector 4, the out quaternion, is again, I'm going to slurp between these two. So rot 1, rot 2, and then the bias channel. And then, as I did before, I'm going to qrotate P by my out quaternion. And then let's create that bias channel. And now if I do this, I'm doing a full rotation of 180 degrees around Z, and I can cleanly blend between this. And if I change the axis or whatever, this thing, again, it doesn't care. It will always find the smoothest path between any two orientations that I define. And that's the magic of quaternions. And in Houdini, because they give you the ability to do this with matrices, you might lose some sense of how awesome this is. Like, this is really one of the most powerful things that quaternions are a necessity for doing this kind of work. Houdini thankfully abstracts, and MOPs also abstract some of this away from you, so you don't have to think about it as much. But this ability to smoothly blend between interpolations is huge. So another thing to point out, and we kind of alluded to this before, is that quaternions and 3x3 matrices largely mean very similar things. They both can describe orientations. So really quickly, let's just copy this Vex that we did here, all this stuff at the beginning here, except what we did at the end. So I'm just going to copy these first 5 lines, and then let's paste them here. And so in this example here, you can see that I've packed this pig head. So I have a single packed primitive with a packed transform. And I want to take this quaternion orientation that I did and apply this to the transform matrix. So the way that I can do this is by taking this quaternion and converting it back into a transform matrix. And that's done using a function called qConvert. So I'm going to say matrix 3, because I'm setting the 3x3 matrix on this packed primitive now. M is equal to qConvert, and then the output here. So this is taking our blended interpolation. Let's turn this on. And let's say, we can do, again, like a 180-degree rotation around Z. So now I have this new orientation defined. And so what I can do is say set prim intrinsic the same way I did before to update the packed primitive intrinsic, because this pig is packed. I am setting the transform intrinsic for the current point, and I'm setting it to this new matrix 3M that I've defined. And now when I scrub the bias, you can see that it's updating the transform intrinsic of this one packed primitive instead of just multiplying or q-rotating P. Let's go over here, and let's literally just copy. We can just copy this node directly exactly, paste it here, and just delete that stand-in and plug it here. So we're going to do exactly the same operation, right? But in this case, check this out. I'm converting this peg head, and then I'm using MOPs transform to scale it up by double. If I take this quaternion, and I do all this great slurping and everything, and then try to apply it back as a matrix, when I put the display flag on here, the orientation is right, but the scale is gone. And the reason for that, and this is why quaternions are used to blend between things, but when you're actually storing data and computing like the final transformers of things, you're still always using matrices. And that's because quaternions can only describe orientations in any useful way. They can't encode scale the way that a matrix can. So this is a big gap. Like we can do all of this great blending, without getting matrices involved because quaternions are so cool, but they can't encode scale. So what we can do instead, if we, again, in later versions of Houdini, we can just slurp and not think about it. But when you're thinking about this in terms of quaternions, what you can do instead, and just we're going all the way to the last example here, we've got our pig head here, he's scaled up and we've got a 30-degree rotation on him. And what we want to do for this last example is apply like an additional rotation on top of that. So what we're going to do at the beginning here is roughly the same as what we have been doing, right? So I'm going to define an angle, so float angle, angle. I'm going to define an axis, normalize CHV axis. I'm going to describe my two quaternions. So the first rotation, sort of my default rotation, is going to be quaternion ident, same as I'm always doing here. And the second one is going to be quaternion, radians, angle, and axis. So I'm creating an angle axis quaternion out of these parameters that I've set here. So let's just set the angle again to 180, and let's make this a rotation around Z. And now I'm going to create my output quaternion. This is exactly the same as what I was doing before. And that output quaternion is going to be slurping between our identity quaternion and the angle axis quaternion that we're defining, and blended by a bias channel, which I'll set here. Set that to 1. And now what I want to do is I'm going to convert this quaternion into an angle axis vector. So another way that you can describe a rotation in Houdini that if you've ever looked at the W attribute in a particle simulation, or target W, this is a common place where you'll see things described in angle axis vector notation. Rather than describe it as a quaternion, which is really only describing like an orientation, something like W, which in particle simulations in Houdini is the spin. So it's not just describing an orientation, it's describing angular velocity. The advantage of using, there's a lot of advantages to using that, but one of them is that you can describe an amount of a magnitude as well as just an orientation, and you can describe it in just 3 terms instead of having to use 4 or 9 or whatever. The way it works is an angle axis vector as opposed to an angle axis quaternion. The direction of spin, or the orientation, is defined by the normalized vector. The amount of spin, basically the amount of force, is the magnitude of that vector. So that's how it's being encoded, is the length of the vector describes the amount of rotation or the amount of spin that's happening, and the direction of the vector describes your axis. That's your axis for rotation. The way that you can take an orientation like a quaternion and convert it is just by, again, using qConvert, but you give Vex the hint that you want to convert this into a vector and rather than a matrix or something else. So if I say vector, we'll call this ROT, is equal to qConvert out. So this is taking our quaternion and turning it into an axis angle representation. Next, I can extract the angle and the axis from this. Let's say our axis is equal to normalize ROT. So this is taking that angle axis vector and stripping out the magnitude part of it. So this is just getting us the axis of rotation. And now to get the amount of rotation, so this is the angle part, I can say float our angle equals the length of that quaternion, of that vector that I've converted. So that's giving me the angle. So now that I have an axis and an angle, what I can do is take this quaternion that I've blended and apply this to the matrix as a rotation using angle axis notation like we were before. So again, I have to fetch the original matrix here. So matrix 3M equals same prim intrinsic function we've always used. I'm going to grab the transform intrinsic from the current point number. And then I'm going to use rotate to rotate that matrix by R angle and R axis. So these values that we pulled out of that quaternion using qConvert, and then just use set prim intrinsic to set these values right back. So I'm going to set the transform intrinsic of the current point number. I'm going to set it to this new matrix M that I've just output. And the result is that I get this, again, just to drive this home, I get this scaled pig head rotated, and he maintains his scale. And this is not something that you would be able to do if you were just directly converting the quaternion to a matrix. You would lose that ability. So this is another way of looking at this, of taking that information that you got from blending these quaternions together and encoding them in a way in which you can use them. In practice, now that we have the ability to directly slurp matrices in Houdini, this is less necessary to do, but I still think it's an important thing to have in your back pocket, and also to just help differentiate between what quaternions are good at versus what matrices are good at. Does anyone have any questions about this before we wrap this up? Because there's one more quick section I want to go into. Okay, I know quaternions are really confusing. I recommend not trying that hard to understand them because unless you're really good with imaginary numbers, they're just really difficult to wrap your head around. But worthwhile. I included a link in the comments in the stickers for the quaternion section to a 3 blue 1 brown video that also has a link to an interactive app that tries its best to explain to you what the stuff actually means. It's still hard, but from a practical standpoint, as long as you know how to use these Vex functions and you know the difference between quaternions and matrices, you can still use them just fine and not think too hard about it. So the last section that I want to go into is called extraction. And this is just a quick thing to sort of explain, once you've got all these numbers encoded in a matrix, how do you get something intuitive back out of them again? Because sometimes you don't want a matrix. Sometimes you want vectors, or you want to be able to see this a different way. So in this first example, I've got the usual pig heads, copy to points, whatever. Now, let's say that from these, I want to get n and up vectors, right? Like I want to know what n is or what up is for each of these points, and I don't have that. Now with MOPs, you just use MOPs extract attributes. That's what it's for. But if you want to do this manually for some reason, this is how it would work. So in Vex, I'm first going to grab the matrix like I have been. So I'm just going to run prim intrinsic to get that 3x3 transform matrix. And in order to basically extract n or up from this, there's a couple of different ways that you can do it. But the way that I like to think about it is basically applying the transformation of our matrix to world n or world up. And the way that you do that is through multiplying, like with anything else. So I can just say v at n, so I'm going to bind this to the n attribute, is equal to the matrix times world n. So world n, you normally think of as our forward direction, is positive z. And then up is just equal to the same matrix times 0, 1, 0, world up. If I do that and then look at the spreadsheet, you can see that n is equal to positive y, which is correct. All these pigs are facing positive y, and the top of the pig's head is pointing towards negative z. So it's extracting the right values, and we could use this n and up to do velocity setups for a sim, or if we just need to like orient other things to match this, like now we have that data ready to go. Just to go to the next concept here, again, I've got these pig heads copied to points, and I'm running them through a MOPs randomize to just scramble the orientation of these points. You can use basically the same exact technique with quaternions if you have an orient attribute and you need to extract vectors from it. So in this case, I'm going to say v at n is equal to qrotate, again, because we're going to rotate a vector by this orientation quaternion. P dot at orient is the orient attribute that MOPs randomize generates when it randomizes the orientation of these things. And then I'm going to rotate, again, world z by this same vector. And I'm going to do the same thing for up. So qrotate orient by world y. And if I do this, you can see that I'm getting n and up vectors that are all sort of, various random scrambled vectors here. But if I turn on normal visualization, I might have to delete the points here to be able to see them. Yeah, there we go. And then I'll template this. But you can see that for each of these pig heads, that normal vector is facing right down the nose. So this is how you can kind of pull different kinds of data from matrices or quaternions. There's one last function that I want to go into that's a little bit more complicated. But there's a way to get even more data out of a matrix, especially something like scale, or if you care about the translate section of a matrix, or if you care about, for example, the Euler angles that you would rotate something to using a transform SOP or a MOPs transform that would get you to a given orientation, you can extract that. I can't really explain to you how to do that from a math standpoint, but Houdini gives us a very great convenience function to handle that called crack transform. It's a little unwieldy to use, but I'll try to explain it here. I recommend looking at the docs for it because it's a bit weird. So again, I am copying stuff to points here. So I've got this usual grid of pig heads, and I'm randomizing position, orientation, and uniform scale for all of these pig heads. And what I want to do is take this information and extract it. And right now I'm kind of cheating. MOPs is doing this for you. It's like generating all these attributes. So I'm just to clean this up, I'm gonna attribute delete and just remove orient, p scale. I don't want to see it. We're gonna pull these out ourselves. So in this wrangle, what I want to do first is, because I'm extracting position as well, just for kicks, I want to get the full matrix. So I'm going to say matrix M is equal to get packed transform, which is our shortcut for just getting the full transform intrinsic from whatever this operator is. So here we go. And now crack transform is one of those magical Vex functions that if you look at the docs for it, it has a lot of overloads that have that ampersand for parameters, right? So it will write to multiple arguments that you pass into it. So what I need to do is I'm going to be getting my translate, rotate, and scale back as vectors. And so I'm going to create temporary variables to house each of these things. So I'm going to say vector translate, vector rotate, vector scale. So these are just 3 temporary holders for where these values are going to go when I run crack transform. The other thing that I want to do is define a pivot for each of these, but the pivot for each one of these things, the way that we have it set up right now, is effectively the center point for each of these packed primitives. So for the purposes of cracked transform, I can just say that the pivot is 0 because it wants the pivot in the local space of each of these objects, and the pivot is at the centroid. If you looked at the pivot intrinsic for each of these, it would be 0. So we don't need to change this at all. And now the last thing is to actually run this gigantic function. So crack transform, you need to read the docs to understand how this function works because it's very strange. But essentially what it's looking for is it wants to know the first argument is what order you want to handle translate, rotate, and scale in. 0 is sort of the default, what you would expect. And there's other ones that you can look at, but you have to look at the docs to know what these numbers correlate to. So like 1, I think it's like rotate, translate, scale or something. It's all very strange, but you have to get this from the docs. I'm going to stick with 0 for this. That's like the default expected. The second argument is the rotate order. And again, it's something that you have to look at the docs to get. But what it's going to, the rotate order is essential for extracting rotations, because if you want to get the rotation written out as Eulers, so as angles like along this much along X, this much along Y, this much along Z, the order matters. Because as all of you know, if you've ever rigged anything, like if you have a wrist that where the rotate order is like X, Y, Z, and like you move the wrist 90 degrees and like try to rotate down and all of a sudden it gimbal locks and starts flipping, like that order matters and has to be like very specific for any given joint or rotation. 0 is the default X, Y, Z that most transforms start with by default, but there are reasons why you might want a different rotate order. So keep that in mind when you run this. Then it wants the pivot, which is 0, but we're just going to put it in here to make it more readable. Then we pass it the matrix. And then the last 3 terms are essentially the outputs. So we're going to write the translates to translate, the rotates to rotate, and the scales to scale. So now what I'm going to do is take these translate, rotate, scale values that I generated and just bind them to variables so that we can see them in the spreadsheet. So I'm going to say I like to, when I'm making temporary variables that are just for debugging, I do this a lot with HDAs especially, I prefix them with 2 underscores to imply that it's temporary. So I'm going to say @__p is equal to translate. And the reason I do it this way is because if I'm wrapping up an HDA or some other tool, and I'm making a lot of like debugging variables so that I can kind of see what's happening in the spreadsheet as data flows through it. Later on, what I can do is drop down an attribute delete and just say __*. And that means it just automatically wipes out all temporary variables, and I don't have to worry about individually identifying them. It's just a handy trick when you're building tools in general. And then R is equal to rotate and S is equal to scale. And when I run this, you can see that the temporary P value here matches my actual P exactly. They're the same number. And then what you're getting here for R are you're getting values between -360 and 360 because these are Euler rotations in X, Y, Z. So you could take these values and apply these the same with a transform SOP the same way if you had your pivots configured correctly and it would match. And then my scale vectors are here as the last one. And that is everything. That is as far as I was planning on going with this math lesson. And we still have a little bit of time left. So if anyone has any extra questions or they want clarification on any of this, again, MOPS is doing a lot of this. Like these same concepts, MOPS is doing them under the hood for a lot of different operations. And so if you want some insight into how some of this looks practically, MOPS is open source, so you can crack open, MOPS transform, MOPS pivot, MOPS apply attributes is really complicated because it's trying to handle a lot of different cases, but it's a good way of kind of seeing like how some of these things conceptually work under the hood. You could take what we had built earlier when we were doing like building our own aim constraint and wrap that up as an HDA. And if you had it reading MOPS fall off as a bias, it would be roughly the aim modifier. You can. Knowing how these concepts work under the hood, if you wanted to, and I encourage that you do, you could build on top of MOPS, maybe use apply attributes to sort of abstract away some of the worst of this so that you know that your fall offs are going to work as expected and all that stuff is kind of built in for you. But these same concepts, because so much of MOPS is about translate, rotate, scale, and applying those concepts in different ways. I highly recommend that you crack open the notes just to like learn better how they work and sort of what they're doing and how it relates to all these concepts I'm going over, and also to potentially use them to build your own tools. If you come up with something really cool and you want to push it to the repository, I accept pull requests. You're more than welcome to contribute. It's an open project. I'm hoping that with more people really learning how it works under the hood, that we can sort of expand it into a broader tool set over time.
Putting a link into the chat there for everyone too. That file, math.h, actually has all of those, the TRS and the XYZ information. So the 0, 1, 2, 3, like the explanation of all of that.
Yeah, and the documentation for the crack transform function will link you to that same file path.
Yep.
But it's not something that you're ever going to get unfortunately, without cracking open that file. But thankfully, most of the time when you're using crack transform, it's zeros all the way down, and you just have to remember what the C term for like what thing you want to extract. 90% of the time, that's all you need. Sure. That's a big topic. So there's a lot of stuff in the Houdini documentation about building HDAs and things like how to namespace things, that sort of thing, which is extremely important. That's the first thing that I would do if you're wrapping up an HDA is like namespace everything. so that you don't get name clashes with other people's operators. And that's, if you were, for example, if you were to look at, I'm not still sharing my screen. Let me open this up real quick. For example, MOPs randomize here. Something that you should all know about in general in Houdini, I leave this open all the time, is if you go to your assets tab and go to the asset manager, if you go over here to the configuration tab, there's something here called the asset definition toolbar. And by default on most Houdini installs, it's turned off. What you want to do is set this to show always. And what that gets you is this tab up here that gives you the asset name and path. So this lets you see what OTL is this? Like what file on disk am I loading this from? Or is it embedded? And it also, this dropdown lets you select versions. So if you have multiple versions of an HDA that you're developing over time and you want to kind of be able to like step through them, I do this, you can see that there's a randomize 1.0 and a randomize 1.1. When you're developing a toolkit and you plan on people on sustaining it, and people are going to be using it for the long term, anytime you make a change to something that significantly could change the parameter layout or what those parameters do, what you do is you bump up that version, and labs tools actually have some stuff to handle asset management for you that I recommend looking into, SideFX Labs. But if you right click on something and go to it in the asset manager and go to the operator list, you can see that the MOPs randomize HDA has these two definitions built in. And I can right click this and duplicate it and then give it a new name. And so I could just give it, and this is where namespacing comes in. The operator name, I could change this to 1.2. But the way that you separate this is with 2 colons. And so what you would want is sort of your facility name or your name or whatever you're going to develop under, the name of the toolkit. For me, it's MOPs. And then the name of the descriptive name of the operator. And then after that, a major and minor version number. And what this allows you to do is make sure that anytime the namespace means that your tools won't clash with other people's, which is really important. But it also means that the major minor version thing means that anytime you change something where if it's not a bug fix, if it's something that's significantly going to impact people's files, those definitions remain separate. So if somebody has an old HDA that's using version 1, even if they upgrade to the latest version of your tool set, those definitions stay where they were until the user explicitly goes back and changes it or drops a new node. So that's number one, like definitely pay attention to that when you're building these things out. As far as like configuring packages and stuff like that, really, if you look at MOPs, the way that the directories are laid out, where you can feel free to use MOPs as an example. There's a lot of free toolkits out there, and some of them are using more old school methods of package management, and some of them are more new school. I try to keep MOPs pretty new school because I think packages are sort of the way forward for how this works. But if I go to my projects tab and look inside MOPs here, you can see that there's an icons tab, there's an OTLs tab, scripts, toolbar. All these are standard. So when you're building out a package, if you want the easiest possible way to get it loaded into a facility, you need to put everything in a single directory and then have it broken out by OTLs. All your HDAs go here. Toolbar, your shelves go here. Scripts, and then within scripts, you can either do, I think there's something else for like command line scripts like hscript, and then for Python, so script/Python, all of your Python libraries go in here. And if you build it this way with this exact directory structure, like named 100% the same way when you build it, all you need to do to get a user to have this in is to have them add this root path to Houdini path. And they can do that either through the env or they can do it through a package file. But that means that it's a one key instead of having to set like Houdini OTL scan path and Houdini toolbar path and all these other like individualized environment variables that are a nightmare to keep together in your head. If you set up your directory exactly this way, everything just works with a single key. So that's another thing that I would recommend if you're going to build something out like this. Otherwise, it's hard for me to sort of describe all of the things that I've screwed up over time, like make backups, use Git for source control, which I can't go into that here. It's kind of annoying to work with, but you have to learn it if you're going to develop software. Make lots of backups.
Another question in the chat here about would an HDA that uses MOPs nodes work in Unreal?
That's a good question. And it should, assuming that the Unreal environment is configured so that it can see those HDAs. So if the environment is the same, MOPS is all Vex under the hood, so it should work. But the only thing that would make it weird is if your environment weren't configured to work directly, like if it was having trouble seeing those HDAs for some reason. I don't have a ton of experience with Unreal Engine. I've used some MOPS nodes in HDA wrappers in Unity, and it seems to work. But somebody who's more Unreal focused would probably have better answers on that than me. And Vic is asking about a MOPS Plus course. I am working on new tutorials. I got kind of thrown for a loop because there's just been a lot of other development in MOPS and MOPS Plus, and I got a day job and everything else. So tutorial video production slowed down a little bit, but I do have more in the works. I need to do, there are already a lot. If you go to the MOPS YouTube page, there are a number of tutorials about individual MOPS Plus nodes that I recommend watching. I haven't completed that series yet. There's a lot more ground to cover, especially when it comes to MOPS DOPS, like the whole physics system that you can use. The next tutorial I do is going to be MOPS DOPS for sure, because that's like a big missing piece. But I'm not going to do those here because I don't want to charge people for it. That's double dipping. I'm not going to charge people for software I'm already charging money for tutorials. So when they come out, they'll be on the MOPS YouTube channel. So I recommend subscribing if you want to know when those are coming out right away. And I post all this stuff to Twitter all the time, so you'll be seeing more of that too.
Very cool. Any other questions? You're getting lots of love in the chat.
Yeah, I appreciate it. And you guys are welcome to speak up if you want to. You don't have to use the chat. I'm done talking.
You can unmute yourself.
Brilliant class.
Thank you. Appreciate that. Yeah, your take on matrices and quaternions was actually very interesting. The matrix, especially, it was a nice different perspective that kind of opened up a few more doors in my brain.
Yeah, and I'll admit my perspective is pretty uneducated. Like in terms of formal math training, I had to teach all of this stuff to myself. Basically, when I started developing MOPS, I was like, "Oh, this is going to be easy." Me and Moritz are just like skipping on a playground or whatever, and it ended up being really hard. That's great to hear. Yeah, I mean, and again, if you run into things that you're used to that are easier elsewhere, or there's like specific problems that you're trying to solve that you think would be better generalized as like a broader tool, come find me. You can talk to me on Discord, you can talk to me on Twitter. Like I'm constant, new tools when I develop them tend to go into MOPS Plus, but things that already are tightly integrated with the base system, I am still developing it constantly. I'm doing bug fixes. I'll occasionally add new stuff to it where it's stuff that's just like really obvious extensions of existing tools that need to be there. So suggestions are totally welcome. If you have them and you're not a developer yourself, you're not about to do pull requests, like just reach out and talk to me. And that includes both MOPS and MOPS Plus. Like if you feel like something is missing in either part, just come talk to me. And I mean it. Feel free to reach out to me if you have questions or suggestions or anything. Like I'm happy to help people with this stuff.
Yeah, definitely post to the Discord and stuff too if there's questions, and even artwork too. Anything that you build, Deb loves to see everybody's artwork. We'll share it across all social media.
All right, well, that's it. Take it easy, everybody.